Okay. Very good morning to everyone. Looks like the coffee wasn't good. Okay, so welcome to the workshop on computer systems and machine learning. Hopefully, you all are enjoying the stay, not stay, I mean, whatever time you spent in IISc. So, how many of you are coming to IISc for the first time? Okay, good. Many of you. Good. Okay, so to surprise you, let's have a test. So, how many of you are from Bangalore? Many of you, right? Okay. So don't worry, you will not be graded in the test. So I will show you some image, I will flash you some image in front of you, and then you have to tell me what image is this. If you are from Bangalore, you should answer this, okay? So what is this image of? Okay. So some speakers also probably have seen this yesterday itself. And then Kavan Park, are you sure? Okay. Fine. I thought that somebody will tell Lal Bagh. Fine. Then let's move on. Looks like many people visit Kavan Park regularly. Okay. What is this image of? UBCT. Oh, see? So you buy things from UBCT? So non-Bangaloreans. UBCT is a place where we all do window shopping. Like one watch or one handbag is probably 1 lakh rupees. Okay? It's Vijay Mallya's mall. I mean, I don't know whether it is any longer Vijay Mallya's or not. Okay, so what is this image of? Okay, thank God. If you were told something wrong, then you would have thrown out of the auditorium. Okay, so I mean, again, I know this was a fun game, but what are these images? Can anybody tell like what is this image or what? Yes. So how many of you have like Ghiblified yourselves or some other image? Yeah, you can raise your hand. Why are you shying? Okay, so many of you, right? Now, how did you do that? ChatGPT. Okay, apart from ChatGPT. Sorry. Okay, then Gemini. Okay, fine. So that actually relates to the workshop. So why we are having this workshop, why we are having so many speakers. So we all know ChatGPT. This is an online solution to almost everything. Previously, we used to take our assignment solution from Google or Stack Overflow. Now we are taking from ChatGPT, right? Many people are nodding their head. This was a trick question, by the way. So yeah, we are all amazed by like what ChatGPT or any of the generative AI application can do. But do we really need to be so much proud of that? Probably not. I'll give you or I'll show you some statistics. So many of you might know that the algorithms like which are actually aiding the all those agentic AI applications, for example, ChatGPT, Gemini, Copilot. I have to take all the company's name, otherwise the sponsors might become sad. They are executed on high performance servers, right? So most of the high performance servers are equipped with state of the art GPUs. That's why NVIDIA stocks are going very high, not other AI companies stocks are going very high, okay? But then some statistics says that the estimated power consumption by ChatGPT in January 2023, when it was first came into public, was between 11 lakhs to 233 lakhs of kilowatt hour. Okay, and it's huge. So just to give you some idea how huge it is, that much power consumption is equivalent to power consumption of 1.75 lakhs of people. If we dig deep, that's equivalent to a daily carbon footprint of around 24 kilogram of carbon dioxide per day. And we are just talking about inference, means whenever you are copy pasting your homework solution, whenever you are copy paste or whenever you are asking to generate or give the images, that's an inference, okay? And all over the world, people are doing billions or trillions of inference, and that's the result. The daily carbon footprint is 24 kilogram of carbon dioxide per day. Let's take it further. That's equivalent to cutting 406 trees every day. So many of you told that you are coming IISc for the first time. So what is the thing you liked so far in IISc? Sorry? Scenery. Greenery, okay. What else? Openness, okay. Which college you are from? PS is not open. So who is talking? Can you raise your hand? You. Okay. PS is not open.
It is, but there are all these people over here. It's more empty and nice.
Okay, fine. So yeah, greenery, and if we let ChatGPT run like it is running nowadays, it will just take, I mean, there are total 22,000 trees in IISc. It will just take less than 2 months to cut down all of them. That means if you come for this workshop next year, there will be no trees at IISc. Of course, there will be trees, but what I am trying to say is, yes, there are algorithms, there are things, there are applications which are doing wonder, but we need to know that are they really worth, or if we want to make it worth, what should we do? Like, we should make better algorithms which will probably be more energy efficient. For that, we need to know how to actually create those algorithms. We need to know the theory behind them. Now, after you create the algorithms, like what kind of systems you want to use to run those algorithms. Nowadays, GPUs are used to execute those algorithms, but are GPUs really needed? Whether is there any other technology? Is there any other type of computers which will be giving you more energy efficient solution? So to answer these questions, or to make you think the answer these questions, we are having this meeting, workshop, conference, whatever you can tell. Hopefully I could make you understand what's the exact scenario or what's the exact purpose of this workshop. Any question? Okay. So just to warm you up, so you are mainly from Bangalore or around Bangalore. So this is the map of India, and if you see the dots or the pins, it's clearly showing that most of the people are from Bangalore. The speakers are from all over the world. Sorry, not world, all over India. And then, so remember few things on the course of workshop. You should take notes. Okay. So all of you got the welcome kit. What's there in the welcome kit? Anyone? Books, pens. So nothing is free. Okay. So we will see how much you can fill all those notebooks, and then based on that we will distribute the certificates. Deal? Okay. Don't worry. We will not do that. But yeah, take notes, and then remember, so you are representing your university or your college, right? And there are many other people who actually applied to come to this workshop, but they couldn't get into, because as you can see, you have limited number of sitting space, right? Take notes, take the experience, go back to your university, tell your friends, tell your batchmates, tell your colleagues that these things happened in the workshop, and these things we should all learn, okay? So that is another purpose of the workshop. So remember, you are actually representing your university or college. So take some knowledge, go back and try to disseminate that knowledge. Ask questions. This is very, very useful, okay, or this is very, very important. So if you will see that all the talks have approximately 1 hour of slot, okay, but speakers will talk about 45 minutes. So there is like at least 10 or 15 minutes of time to ask, to have a good and productive question and answer session. So make use of that session, and of course we have breaks, coffee break, lunch break, etc. Go and talk to the speakers, go interact with them, try to know what are they working on in more detail, and then only you will understand that whatever you are learning in your course, how are they useful eventually, how are they useful in industries and all of them, okay? Then of course interact with speakers, of course interact with other attendees. Let's say, I know many of you are from JSST, so let's say you are from JSS, just don't talk with your friends group, go and talk with other people also, other attendees also, okay? Maybe you will understand a different variety of who knows. Yeah, post your thoughts with hashtags. Our department is present in X. You can just tag with IISc CSA. We are at LinkedIn. You can tag with Computer Science and Automation. We are also live streaming the whole talk. I don't know whether the live streaming is on or not on. On YouTube. Again, if you know someone who is interested to listen to the talks but couldn't make the workshop, you can send the link to them. The link is there on the workshop web page itself. And then yes, so first they have to subscribe to CSA channel. Oh, I don't think they have to subscribe, but if you want to attend more of this kind of workshop, but let's say you are not able to make it in person, you can subscribe to CSA channel IISc, which is the official YouTube channel of our department. You can see what are the upcoming workshop, and if you are interested, you can join those workshop and join the talks online. Now, few logistics. if you have any question, if you are stuck in any gates of IISc, IISc is like Bulbulaya. If you enter IISc, you will have a hard time to get out of IISc. And it doesn't mean that I am not talking about the PhD students. Okay. So spot the volunteers. Okay. So the volunteers will be either in maroon t-shirt. Today we are in maroon, or the blue t-shirt. So we are all volunteers. So with that, this is today's agenda. And remember, ask questions, make notes, and have a wonderful experience so that you can go back and tell this is the things you learned. Questions. Just now I told ask questions. Okay, fine. I hope, so don't ask questions to me. With that, I will welcome the first speaker today. She is Manisha. Manisha Padala is an assistant professor of computer science at IIT Gandhinagar. She received her BTech in electrical engineering from IIT Jodhpur in 2017 and her PhD from IIIT Hyderabad in 2023, during which she interned at Google and Adobe. Her research group works on problems at the intersection of machine learning and fairness, focusing on fairness measures, fair and private classifiers, and fairness in federated settings. The group also applies ideas from mechanism design and deep learning to design systems that are resistant to manipulation while ensuring efficiency and fairness in context of auctions, crowdfunding, and resource allocation. So let's welcome her.
Thank you, Sumit. Good morning, everyone. I hope I'm audible to everyone in the back. So thank you for having me here, and welcome to all of you. So today I'll be talking about some preliminary results that we had in... okay. Okay, while this gets set up, how many of you have some background in machine learning? Okay, not bad, huh? So what is the most important thing about machine learning? What is the integral? ये नहीं हुआ तो you cannot train a model. Data, right? Okay. So that's what is going to be the focus of the motivation of our talk today, right? So what is ChatGPT trained on? What data? Does anybody know? I mean, it is trained on data, right? Or not? Sorry? The internet, right? All the web, all the data that is available on the internet. So it's trained on vast amount of data, which is why it is probably which is why it is as good as it is, right? And like Sumit has said, it has used so much of resources that we could have otherwise used for other things, right? So So the agenda of today's talk is since all of you know what machine learning is, we will try to understand how we can extend that to federated learning, why do we need federated learning, right? And then we will talk of some aspects of federated learning that is not good, and how do we fix those things, right? So that's the goal for today. So how many of you recognize what this is? We are still continuing the game. Data centers, right? So these data centers this is probably one of the Google's data center in the US. So this has a lot of your and my personal data, I guess, I don't know, which Google is exploiting, or maybe it is helping us with that kind of data. So all these models that we are familiar with, how do we train the algorithm? All the data is sitting at one place. We take batches of data from it and we train our model. That's how we do it, right? That's how we do it. So the model that is being trained actually has access to the data, and the global, the server, the person who is training the model also has access to the data. So what is the issue with that? A lot of privacy concerns, right? You are actually sharing your personal data. So that is the first issue with such a centralized training setup. All the data is sitting at one place. People are obviously able to see your data, right? So that is a data privacy issue. And the other thing is, when you want to train large models which are very good, you need lots of data. And data sometimes is not very, maybe you need data from across boundaries or across nations, right? Different nations and different organizations should come together, pool in their data and train a model for a good model, right? That's how ideally it should happen. But of course we have so many practical constraints, right? We cannot, different organizations cannot freely share their data, right? They have their own restrictions in terms of, especially in industries, and also data when traveling across nations, it's not easy. You cannot share your data very freely. So all of these issues are some logistic constraints that come when you wanting to do centralized training. So what can we do? How do we get out of it, right? So what is the, so we don't want to share our data, personal data, right? But we still want to have a model that works well and predicts well for our data. So how do we do it?
Synthetic data?
Synthetic data, but how do we build that synthetic data which is representative of your personal data? Uske liye you will again need to see some sort of personal data, right? So how do you get out of this?
Trying to combine data from the owners of data and putting it into servers so that it cannot be decoded by the server itself.
Good, good. So what you are saying is some sort of encryption, right? You encrypt the data and put it in the servers, and then, sorry.
We can train the model and then unlearn some privacy related data. Unlearning of person.
You train the, but while training itself, who is training? A third party is training, right? You're not the one who is training. So the one who is training itself will have the data information already. Right? We don't want that also. Encryption is, on the other hand, somewhat of a reasonable way to do. You encrypt all your data, you send it to the server, and you have some way of training. I'm not very familiar with how such kind of a model works, but there are results which shows that once the model is trained, right? Once the model is trained, you can easily get back what you are training from the model, what your input would have been, even though the unencrypted input. And maybe there are some other issues, or maybe this is a good approach. I don't know. Any other ideas?
Training the model in the local event.
Ah, very good. That is what is the agenda for today. Any other ideas?
Anonymize the data such that it doesn't have personal information.
Very good, very good. That's, I think, one of the Netflix attacks, right? They anonymized the movie rating data, and people linked that anonymous data to IMDb's data and figured out who the owners were. So there is so much of data out there in the internet that anonymizing helps, of course, to some extent, but not a very foolproof plan. Knowledge distillation. What is that?
You have a teacher model, so you provide the entire model which has been trained on the data to someone, and then they can train extreme model, a smaller model, a weaker model against that, and they try to get as close accuracy to the parent model as possible, but trained on their own data.
So how do you get the teacher model? From publicly available data? Is that yours? Okay, something like that. Maybe that works. Maybe that's what people do nowadays, I guess. You take your ChatGPT and fine tune on your personal data, right? But what if you want to train a global model or the teacher model itself on everybody's data? Is there another way to do it? So that's what we will see today, and that is what is federated learning. So back in 2017, people from Google, McMahon is the only name I remember from the paper, so they proposed this idea of federated learning, right? So we all use, how many of you really type the entire text in your, while you're chatting? You want to be very fast, right? Nowadays people are even more quicker at texting than I am. So I'm sure you use the predictions that the model gives. It already knows, oh, this is what you're going to probably type, right? And your chats are, how many of you are willing to show me your chats, right? Can I open your WhatsApp and see? No. So it's a very private information, right? Nobody wants to share their personal chats. So Gboard, Google Keyboard is the first place where federated learning was implemented. So Google cannot collect your personal chats and train a model so that it is able to predict the next word well. So the task that it wants to solve is to predict the next word given the current existing words. And it cannot take your data somewhere. So what does it do? So it does the following. So first of all, we have a language model. Back in 2017, we didn't have transformers or anything. It's a small RNN or LSTM kind of a small language model, right? They use that for next word prediction. And instead of taking the data, they deploy a small model into your device, right? Into your device. Now, this small model is only trained on your data. And you are probably not chatting a lot, right? You are probably chatting very sparsely and you have very small amount of data that the model can be trained on. So it probably won't be as good, right? You ideally want the model to be trained on large amounts of data. So what do? So they train these large models on each device's data, millions of users, right? Millions of users using this particular application, and models are being trained on each of these devices locally. But instead of sharing the data, the model updates are shared, right? So you do not directly share the data, you share the model updates. And then you aggregate these model updates at a central level. So this is a preliminary idea of what federated learning looks like, right? So this is the paper, and they first showed their application in mobile keyword prediction, right? So how does this work? So you could think of it as an abstract two agent setup. One is the server and the other is the clients that are participating, right? So all these clients have personal data which is local and private to them. They do not need to share. But the model, so in the first round, what happens is a model is initialized. It could be your favorite deep learning model, which is initialized randomly, right? And it is shared with all the servers, clients, right? And each client locally trains the model on the local data. So the weights or the parameters in the model will be different for each of the client, right? They won't be the same, right? But now what I want is a global common model, the nice global model which is apparently trained on the whole data on all of the clients. So how do we get it? So we collect back these models, right? And all these three models are different. We have to have a way of combining these three models into one big global model. Okay? So that's what we want. So any doubts in the setup? Any questions? Or any comments? Do you think it's too simple?
What if a new user join? What model they?
What model do you use or what aggregator?
Assume that 3 users are already there in the chain. New users join the chain. Do they get the aggregated model or the initialized model only? They need to train again by themselves?
Right. So the idea is that once the model is aggregated, you send this aggregated model again to the users for further training. Whoever is joining now will get the current global model.
Whoever has their own trained model, it replaced with the...
It is replaced with that, but they have their own data, right? And they can now update this model with their personal data further. Again, things will diverge, right? Again, people will end up with new models. Again, you bring it back to the server, aggregate, and you keep repeating this process till you are fine with the performance of the global model. And like you mentioned, not every client will be active at every time, right? Not everybody is texting all the time. So we do this process only with the ones who are active, right? That's how it works.
What about aggregation? How will the
Yeah,
aggregation
that's a good question. How would you want to aggregate, let's say?
immediately something like sample mean sort of idea?
That's it. That's it, I guess. So that's how simple it is. So this is what we do. So this is the gradient descent update step, right? So every model is taking the current, whatever is the weights, and doing one step, let's say some couple of iterations of gradient descent, right? And it's getting a next new model, right? W3T plus 1, which is the new model. So you collect all these new models and you aggregate. You take a weighted average. If the first client has very few samples, then the importance of that particular weight is less. But if a client has large number of samples, then you give more weightage to its models, right? So to do this, what does the server need to know? The server needs to know what the models are, right? The new updated models. It also needs to know how many samples each of these clients have trained on, right? With both of this information, it is now able to find a global model. It does not need to know the local X. So this is the, so with this, what kind of back in 2017, what kind of performance did they show? They used it for emoji prediction, right? So now the prediction for emojis was 7% more accurate than before, right? Than when you were only using your personal data, it was less by 7%. Having global information helps. So also, what is prediction strip? So you have some bunch of words that you would likely, so how are you question mark is the prediction strip. So now maybe at some point I was not very good at English, but somebody somewhere in the world is very good at English, and they, after using this particular word, have a very nice sequence of words that they used, right, which I never would have used. But because it has been globally trained, right, because it has been trained in a federated way, the suggestions are now very appealing to me. Just like ChatGPT, now we don't write our own mails, right? We just let it write it for us. So now people have started clicking more on the recommendations because the recommendations are more appealing to them. So people have, the click rate increased by 4% for predictions, and 11% more started sharing emojis, right? Very early on, we were not very comfortable with sharing emojis, but with use and with many people using these recommendations, we became more used to it, right? So this is how you increase your market. So this is from a subsequent paper which worked on that. And you could apply this to any other application as well. For example, action prediction. You want to suggest a GIF, a sticker, or a search query in the next particular thing. So these are some of the results. 47% reduction in unhelpful suggestions and so on. So it seemed to work, at least for Google. And this caught up with, so the other industries as well caught up with this. And for example, Apple started using it for voice recognition, right? So that was a major issue with Siri, but now when it is trained globally on different kinds of voices, different accents, it started to perform better. Right? And the other major application is in the health industry, right? So in health industry, the major issue is each hospital has access to some limited set of patients, and that's a very private information. It cannot share it across hospitals. Uske alawa, other than that, the actually very high risk patients are very few compared to the volume of a patients any hospital gets. So the data set where they can see the positive information that there is a disease or whatever, right, is very less. So that pattern, to learn that pattern, you need to be able to learn it from very small data, or you need to from somewhere get more such positive sample data, right? So which is why and so couple of American universities got together and they used NVIDIA's Clara federated learning platform, and they build a collaborative training for mammogram assessment, right? So they build a kind of a classifier here. So where different university hospitals will have different data, and when you pull it in, instead of pulling the data directly because you can't do that due to constraints, you try to deploy an FL set of there, right? So that's where they use that. And similarly for Pennsylvania, etc., they used Intel for brain tumor detection. So these are some of the applications. Other than that, people also use it for autonomous driving, right? So different landscapes, different lighting conditions, different road conditions, data which is spread. You would want to have a model which can work on all these different conditions, right? So people try to deploy federated learning in these setups. Yes.
You pointed out to a problem of backtracking whatever it was trained on. When I was talking about encryption, right? Like if we have encrypted form of data to a server, then it can perhaps work out the data it was trained on. So how will this not happen in this case?
It will happen in this. It will still happen in this. So you need different privacy guarantees for that. That is my next question, by the way. So is FL nice? Do we overcome all the issues, or does this have some problems yet? Right? So it seems very good, right? Now you don't need to share your data. We give you our models. You train the model. We get the. It is as if the model has been trained on all your data. Seems very nice, right? But like you said, one issue is still the privacy issue is still persistent, probably, right? Because you can still learn your data from the model itself. So FL will need additional privacy constraints, but immediately you're definitely not sharing your data. That is there. Any other concerns do you think could be an issue in this particular kind of model? Or is it?
We have something that weight, right? Weight matrix, weight, we can reverse engineering the way we get the data, right? So then we
Yes,
have
that's
sort of weight.
exactly. So it's not fully guaranteeing privacy. We will need additional privacy setup. Or kuch.
Malicious data. It could be malicious. It could be a fake data.
Yeah, security. Because now there is no one person. There are multiple people involved. Lot of ways of security issues could happen, right? Security issues could be in the form of clients who are malicious, or could be in the form of aggregator who is not trustworthy. He is not aggregating well, but the clients are not sending the correct data. Yes.
Overfitting, like since there are many different machines which are training similar this thing, there might be some case wherein the data or the data gets overlapped with one another.
Overlapped, right. So that will cause, you're saying, overfitting, is it? Okay. I'm not sure, but if the data is same, it's fine, right? If the data is same, the global model will work equally well for all the different clients. But the actual issue is when the data will be very, very different for all the clients.
And you're like in the case of
Driving,
Outliers, yes.
autonomous driving, the road conditions will be very
Very different, very different.
in India and US.
Exactly,
So
exactly.
the II for sample mean we need independent
Very perfect, that's correct, that's absolutely right.
and identical variables.
Exactly. So we are just taking an average of all the models, right? What is the guarantee that it will work on the global data? The guarantee is that only if the data is IID, right? All the clients are sampling from the same distribution independently, then it will work. But that's not the case, right? The way you chat is very different from the way I chat, right? The kind of sequences or sentences or intentions, everything is very different. So how do we now, does just averaging guarantee that it will work well for all of us? Right? That's the question. Any other issues?
Constraints on the model.
Constraints. Example?
Like you can't have a very big model on the edge devices.
Very true. Very true. That is completely true. You cannot have very big model on the edge devices. Yes. That is something I have not thought of yet. So that's a nice thing. So you would need some sort of a tiny model, right? Some sort of a way of training tiny model. Any other? Okay, these are enough, I guess. So, of course, there are some issues related to communication costs and other logistics, right? Every model, how much time do you spend aggregating, right? And communicating with all these models, how many models are available at every time, and you are actually communicating a very large model, let's say, then it will take a lot of cost, right? So you need to be able to optimize all of these. The other issue is data heterogeneity. Data spread across agents are not the same. It's very different. So how do we handle that issue? The other issue is this is something that we've included. So this is incentives to participate. So let's say there is a hospital which is very good, right? Very high quality data. But there are 10 other hospitals which are not that great. They are having some very low quality data. So the global model's performance is largely being governed by one particular client, and the rest of the clients are just there for free, right? They are just getting the benefit of the global model. So what is the incentive for this large hospital to actually be a part of that system, right? It will just break off. Right? There is no incentive for it to contribute. It is spending a lot of money by doing local training, communication, all of that, collecting data, all of that is an investment, right? Why will it invest? So that is so how do we incentivize people correctly so that they are a part of the system and eventually all of them grow, right? That's the goal. So that is one of the issue. The other issue is of course the security issues. People could be malicious and try to harm your global model.
What about the power consumption on the edge device?
Well, that stays the same, I guess. As long as you make some fundamental change in the way you're training the model, like Sumit said, or the way in which your system is designed, whatever we have right now is just distributed, but I think the amount of energy that you consume will somewhat remain the same. That's still there.
In aggregation, is there a way to penalize those who are trying to act malicious?
Exactly, that's what we will see. Okay. So today's talk is about adversarial attack. So today's talk is about malicious clients, right? So how many of you know what an adversarial attack is? Okay, so it's very simple. So this is an image from ImageNet, I guess. Correct me if I'm wrong, right? So we want to make a classifier, build a classifier, image classifier. So we use our standard model, a deep learning model, and it predicts the breed of this particular dog correctly, and it is very confident, right? It is 90% confident, and this is a correct class, okay? So the model is very nice. It is able to predict the breed of the dog with very high confidence. But now I send a different image to that model, right? This is, you'll have to trust me that this is a different image. So what would you classify it as? You would still classify it as the same, right? It doesn't look different. But now for this image, the model gives a very different breed, right? This breed looks nothing like this. And the model is also very confident about it. Right? So it doesn't take much, at least humanly much, for the model to be destabilized. So what is the difference between these two models is noise. There is tiny amount of noise in the image, but the model is completely thrown out of track. So we want to slightly perturb the data to increase the model error. So if any of you is interested, you can visit this website and try it for yourself for a lot of the upcoming the deep learning models. And they also have implemented many different ways of adding noise, right? So what is the idea? How does this attack work, right? So we are today in the attack mode, so we would want to build attacks. So how does this particular attack work? So let's say you are given an x0 and a y0. x0 is the input image that you want to classify, and y0 is the correct ground truth label that is given to you. Now you want the model to classify it as y prime, which is incorrect, which is not the correct ground. This is your goal. So how do you build your attack? So this will be your objective, right? It's a very high level idea. So once you get into the details, there is lot more to it. But the high level idea is that you want to change the input from x0 to x, right? Such that the distance between x and x0 is still small. If the distance is large, maybe the image itself will change, and then it is not a stealthy attack. It is very obvious that the images change, and then maybe the predictions will be correct. So the distance is very small, so that the image still remains as x0, at least for the human eyes. And we want the classification to be with respect to y prime. We want the label to be y prime instead of y0. So we minimize the distance between the new image and the old image, and we also minimize the new loss, where the loss is minimized if the prediction is incorrect, right? So your loss will be with respect to x comma y prime instead of y0. So you're forcing the model to mispredict, right? So this is what the attacker's objective is. Okay? So you could use your favorite distance metric and your favorite classification loss, right, to minimize the error. So how do you train it? You use simple gradient descent, right? So here what is fixed? Your model is fixed. What are you updating? Your input is what is getting updated, right? So it's slightly different from the way your normal learning works. You're learning the input and not for a given particular model, right? So you want to attack a certain model, that model is fixed here, and you want to change the input. So this is there are many such attacks, but this is the primary idea about how these attacks work. And because of this, we are able to get images which are adversarial, and the model is confused about it. Okay? So in the FL setup, such a problem can be aggravated, right? So your clients are malicious. If the clients are malicious, they don't even need to be stealthy, right? They don't even need to ensure that the images are close by or something. They could arbitrarily poison things because poison the data, because anyway the data is not being shared, right? Shared with the. So the goal of the adversary is to manipulate the global model to have high errors, right? What all can it do? It can directly poison its local data so that the global model is thrown off track, or it could directly poison the model itself, right? It could add some poison, add some noise in the model itself, and so that the global aggregate becomes bad. So this is how it works. This is the global model initially sent to all the clients. The clients will update their local models. Maybe the honest clients are having some benign, some nice updates, but the adversary is having some poisoned update. Once you take all these and you aggregate it, you get a poison model. So how do you defend this? Any ideas? How do you detect a poisoned update? Can you even detect a poison? So update is in the, so this is not in the realm of images anymore, right? This is in the realm of model parameters. Okay.
The question is also how much of effect will it have on global? Like, will it be very large? Then it makes sense to.
Very nice. So let's say all the clients are malicious. Then can you even? If all the clients are malicious, then what is normal? So you don't even know what is a normal, what is the honest update, right? So what is the first assumption that you need to have to even make any story out of this? You need to have that whatever is the majority, that is honest. That is all I can do, right? If the majority itself is dishonest, then maybe that is what is honest for me, right? So that is an issue. So assuming that majority of the clients are honest, only the minority are dishonest, how do we now detect the minority? Any idea?
Do we need to detect the minority because it's a minority?
So if it were not malicious, you could have had a very nice model, right? Because they are malicious, whatever accuracy you could have had is now dropping. So you would want to maintain your accuracy. To do that, you need to weed out those clients. Right? So the idea is to improve performance. Right? Even if you may probably, if there is only very 0.1% of your clients are malicious, then maybe you don't want to detect. But if you are able to detect, you will definitely improve your performance, right? So positive thinking. Is there a way to detect and improve the performance?
Instead of using the whole user database, you put them in bins and you look at the accuracy per bin. And when you start putting in malicious users in the bins, the accuracy of that one bin will start dropping.
How do we compute accuracy? So now what you're assuming is that the global mod aggregator has access to some data set where he's able to validate, right? And if that data set is good enough, he might as well use it for training. Right? Assuming that there is no data set with not large enough data set to validate. I mean, the answer won't be very tough, but just to know how you guys are thinking.
We can penalize the adversary, like we can compare the old data, like the updates that are running.
Sure. So compare the adversarial update with what?
With the old data. So
Data?
Like the server which like they have the old data. Like compare it with like
Old model, you mean?
Yeah.
Old model. Yeah, that is something that we can do. Something similar only is what we do. Right? Any other ideas?
After each update, after each update, check how far the model predictions are moving.
Model predictions are okay. Yeah, okay.
Model predictions are how the model is learning based on the weights. If the weights are completely opposite of what has been learning or so far, you can classify that as
Sure.
adversary.
Something similar only is what we do. Agreed. So we have to think of everything in the weight space now, model parameter space. So this is one particular idea. There could be many ideas. So this is one of the famous defender, which is known as Scrum, right? So what it does is the same. You try to find outliers in the model parameter space. Right? So how do you find outliers in the model parameter space? So what do they do is, let's say you have up to F malicious clients. You don't know who those F are. You have N total clients, but you have up to F malicious clients. You don't know who those F are. So to be safe, what you select the updates closest to the N minus. So what you do is you select clients which are, first you compute the global aggregate, right? And since majority of the clients are honest, what you can safely assume is that the global average is leaning towards the honest clients. This is all in the heuristic space, by the way, no guarantees or whatever. So majority of the clients are leaning towards the honest. So to that global aggregate, you find the closest N minus F minus 2 neighbors, assuming that these will be somewhat honest, right? These will be somewhat honest. So the idea is that majority of the clients are honest and the malicious updates are going to be distant. So they have a bit of a way of computing scores for every client. So what they do is, for every model, they compute my closest neighbors, right? For every client update, they compute the closest neighbors. And how far are the closest neighbors to me, right? If the closest neighbors to me are very far, that means I am likely a malicious client, because if I'm part of the majority, then maximum of them will be spreaded close to me, right? If I'm in the minority, then the majority of more than half will be far away from me and very few will be close to me. So the nearest neighbor distance for every client will serve as a score to how much of an outlier you are, right? Seems to work fine. So based on these scores, you select the top N minus F minus 2 or whatever percentage you want to select for aggregation. So instead of aggregating all the models, you compute a score for each of the model. The score indicates how much of an outlier you are. You aggregate all the lowest score models, right? And that's how you defend for it. So for example, these are some of the results from this paper. Yes? Just being safe, I guess. F are malicious, thoda or come I will just use, I guess. I mean, it's a hyperparameter. It's not.
So it's not, there is no guarantee?
There is no guarantee. I mean, in this paper there was no guarantee, but more recently there are few papers who are trying to provide some guarantees, but I'm not sure how good they are.
How are the neighbors selected here for the malicious?
Distance between the model parameters, L2 norm, or yeah, I hope L2 norm, right? This is the.
But like the clients can like the model might be working on like for different tasks.
Very good. So this may not work for when the data is heterogeneous. Right? When the data is heterogeneous, I don't know how good such a scheme is. Maybe you need to come up with something new. I don't know. That's something. Yes.
Suppose there are 10 clients, right? And 6 of them are honest, 4 of them are malicious. But the 4 of them are on the same dishonesty, like same bad values they're propagating.
Okay, so 4 of them are close.
So 4 of them are close, malicious, 6 good values are all pretty close. How will it work then? Because you're also doing it by n minus f minus 2, so that's 10 minus
4 minus 2, which is again 4.
So will it fail?
It will fail. It will fail, I suppose. If all the malicious clients are together, this will fail. Nice.
This whole FL is failure if the server is full.
If the server is?
Yes, server is failed. Like the aggregation is not happening in the server.
Oh, that is absolutely true.
Point of view. Right?
Yeah. Single, exactly. So you need to build a system which is, So there are new papers which propose a multiple aggregator setup also. You don't want to a distributed aggregation.
Cluster based.
No, so there is a multi-party competition. So this is a more systems kind of a paper where you do not compute the aggregation in a single server. You compute the aggregation piecewise in multiple servers and aggregate. So that even if single aggregator is malicious, your overall model won't fail. That's there, but that's a different story. Right? Yes.
So it looks like this is not able to distinguish a malicious node from a node that are just seeing the different input spaces.
Exactly. It won't.
So it may
May or may not. Yeah.
It may slow down the learning in those spaces.
It will. It will definitely. Yes, that is true.
Also,
Yes.
the aspect that this is trying to focus on is how close, if I'm getting it right, is how close it is to its neighbors, right?
Yes.
Now the thing is that there might be some genuine update which might be like far too distinct from whatever the other people in the group are doing. So isn't it better idea to compare how the model was within that same setup before and after, and test if if the update is drastic, if the weights have changed in a drastic manner.
What if the malicious client is malicious from the beginning? I mean, just playing a devil's advocate. Maybe this.
That makes sense, but also then the aspect is that even genuine clients, they might be very far from each other.
Exactly. That is the case where data is heterogeneous. I'm only looking at dog images, you're only looking at cat images. Your model parameters are likely going to be very different from mine, right? Then the distance is anyway large. That is an issue. That is an issue. Yes.
What if weights are too scattered?
Oh, correct. That is also an issue. So there will be one more. So sparse, you mean, right? The weights are very sparse. Right? In which case this doesn't tend to work well, but we have one other algorithm that does. Maybe let's just move a bit. So this is, in this particular thing, for these easy data sets, this seemed to work, right? So this, if you didn't have any adversary, you could have gotten a very good accuracy, right? You could have gotten a very good accuracy. So this is the error rate here. So the errors for when there are 0% clients, when the malicious clients are 0% is very low, right? So the errors are very low. But when you do Fed average and there are 45% clients who are malicious, your error shoots up to 0.6. But with Crumb, it still remains in the same realm as before, even when there are 45% clients who are malicious. But these are like very relatively easier data sets. Oh, I see. Okay, so there are other aggregators as well, right? Trimmed mean. So this is 5 minutes to 45 minutes, right? Okay, so maybe I'll just take 10 more minutes if that's fine. So this is trimmed mean. In trimmed mean, this is a different kind of an aggregator. What it does is that instead of taking a score, it takes a coordinate level. If you imagine the weight vector to be, let's say, of 100 dimensions, right? It's 100 in the 100 dimensional space. Now stack all these client weight vectors one over the other. So you get a n cross 100 kind of a matrix. Every column of this matrix you want to remove the outliers, right? So that even if the weights are sparse, now you are looking at coordinate level outliers and not an overall distance level outliers. So for every coordinate, you pick the very far away values. You only aggregate the median values, and that median value will be populated in your global model. Right? This is one other heuristic people have proposed. So this tends to be a bit stronger, right, than the Crumb. So let's skip all this, but this is the general idea wherein you are trying to find a coordinate level. So the motivation for today's talk was all these attacks, even if they probably are not very good for different setups, even in the setups where they work, they only are preventing attack on the accuracy, right? Accuracy is the only measure that they are attacking and the defenders are defending. What about other notions of measures that people might be interested in? So one notion that we as a group are interested in is the notion of fairness. So what is fairness? I'll just give you a brief idea. So this is the first time where it was detected in the Compass software, right? It is deployed in the US courts. So what does it do? It predicts how likely is a criminal going to commit a crime again, right? It's just predicting based on different features of the criminal. Race, age, his previous record, economic status, location, etc. So many different features you feed into the model. And it was trained only to maximize accuracy. You want to train it so that you are able to detect those criminals who are committing the crime again very well, and you are also able to label the ones who are not committing a crime as they are not committing, because doing it either way would really cause a lot of effect in their personal life. So you don't want to be you don't want to make mistakes then. So in this particular case, what ProPublica is a organization which studied this software and saw its results. So what it found was, on white race, the model had a lot of false negative, right? Even if the person committed a crime, it would predict as it did not, right? So the false negative rate was very high. But on the other side of on the other race, which was African American, the false positive was high. So even if they did not commit the crime, the model would mispredict as they have committed the crime. So this is the kind of bias that perpetuates. And this is something that you cannot do away with, especially when you are only focused on maximizing accuracy. Okay? So for the most accurate model that you could train, this is what you would get. High false negative rates for some and high false positive rates for some. So this is unfair, right, in some sense. So you want these errors to be not very different across different races. You want, probably it will be fair if both races had similar false positive rates and similar false negative rates. So this is what is an additional constraint on top of accuracy that you need to have to make a model fair. So so the idea is, in a federated learning setup, we want to attack the fairness of the model. So we want to make an attack such that such a disparity increases. Can a client do that? Right? How much of a bias can a client introduce? So that is what we wanted to study. So either you could, and we studied it for all these three different aggregators that are there. So the first thing that you could propose is a client could completely mess up one particular race's predictions, right? And keep one particular race's predictions very well. And that would probably introduce some bias, but then that would also hurt your accuracy. The moment your accuracy is low, one of these defenders would detect your model, right? So the idea is you want to maintain the accuracy, but still want to increase the bias. Is it possible? And how do we do it? So that was the goal of the work. So yeah, so maybe I can stop here. If any of you have any doubts, suggestions, or maybe how do you think you would approach this problem, that's also fine.
So
Yes.
there can be issues of bias introduced because there are, say, many more training samples for one class than the other class.
Many more?
Samples.
Yeah, exactly. That is the point. The base rates are, yeah, exactly.
So possibly oversampling or undersampling to get the number of samples equal and then train the model.
So the only issue is not the fact that you have a large amount of certain race, but you have a large amount of certain races samples with a certain kind of prediction. So you will have to so there are some initial methods that do oversampling, right? Of, let's say, you don't have many a race 1 candidates with label 1, right? So you oversample those, but that does not give you a lot of performance. That does not reduce the bias by a large margin. Even if it does, it causes the accuracy to drop a lot more. So even if you are equalizing error rates, but now you are making more error on both of them, then is that really funny? Is that okay? So you want to also balance the error rates, but overall also you want to make lower error. Otherwise, मैं 100% error इस पे भी कर देती हूँ, उस पे भी कर देती हूँ, fair है. It's fair only, but that's not what we want. Good, nice questions. Yes.
So I have a question on this data heterogeneity.
Sure, please go ahead.
So if you have data is completely from different categories, right?
Yes,
In
exactly.
the sense, let's say you are doing a predictor for predicting the length of something.
Okay.
Right? Something in meter, something in centimeter, something in millimeter, right? Basically, the average model is useless for everybody. Right?
Exactly.
So how do you handle such things?
So there is something which is known as personalized federated learning. I mean, this is I'm all spitting out from the existing work. So in personalized federated learning, what you do is you don't look for a global model. So because a global model may not also work well for all, right? Because you have different tasks altogether or some different aspects of the task. So what do we do is, we build a one model. Some of the initial layers are shared across all, so that some aspects of the training is shared, but the final fine-tuning layer is different for each of the clients. So that is personalized FL, which caters to the non-heterogeneity setup. You don't even come up with a global model, but you just come up with a part of the model which is globally trained. So that's how people have tried to handle it for now.
What if instead of aggregating we'll use ensemble learning kind of stuff?
Okay, I see. So you want to do a multiple, some sort of a different kind of an aggregation of all these models. If the local could work. That could work. But now you have to do a much more for every inference. If you have thousands of, so imagine in a mobile network setup, how many clients do you have? So you will have to do an inference for all these thousands and millions of models and then do an aggregation. It's a very costly process, right? But it could probably work in a smaller, maybe in a hospital setup where there are like 5 hospitals collaborating, it could work. But in a, it probably will give you reliability probably at a cost of computation. That is true. It's a good suggestion. Yes.
You were talking about multiple global models in some sense, like you
Aggregators,
yes. So that could increase a lot of things, right? It could increase the cost of computation, it could increase the energy consumption of the computation. So is there any way you're doing some kind of trade-off to balance that in this?
So the thing is, even though there are multiple aggregators, the communication cost might increase because now you're communicating with multiple, but the model remains the same. It's just that each aggregator is now only looking at part of your model. They don't know the whole story. They know only the part of the story. So your computation cost won't increase, but the communication cost will increase. But it is giving you some sort of a security or reliability.
So is there any trade-off that, like any kind of optimization techniques or anything that is being used to balance that?
So the idea for now is just the focus on, the paper that I am referring to or the system that I am referring to is known as FLOCK, F-L-O-C-K, and what it has proposed is that it is just trying to increase the security aspect of it. So to have these security issues, how many minimum number of aggregators do you need so that you can compute the global average faithfully, even though not every aggregator is looking at all the entire model, right? So I'm not sure if they are doing any optimal way of, maybe that could be a good direction to think, right? How do we optimally have a set of aggregators who increase security but at minimum cost, right, to the overall communication? That could be an interesting problem.
So is there any work where a part of the, let's say a hash that identifies which part of the data space you're in is sent along with the weight updates? Now this compromises privacy, but often there is a trade-off in some, let's say some of the contributing agents may be okay with sending that.
Got your questions. How do you denote a part of the data space? How do you capture that information?
Without releasing the data.
Without releasing the data set, agreed. But how does this information look like? I am in this part of. How will a client know which part of the?
Some sort of a hash of all of the input data that kind of can
But to compute that hash, won't you need to know the global data so that you know, oh, by the way, this is this part of the data, that is that part of the data. I'm not sure. This is all me trying to.
Let's say, for example, a midpoint of all the
Oh.
data that was for one point, let's say, just a midpoint of the.
Huh.
So I'm not giving any specific data points, but I'm just giving a midpoint, sort of an average of all the points. And some of the nodes may be okay with that, some may not be, so they can decide.
Very good, very good, very
You
good.
can trust those nodes more than the others.
Very good. So this is something which is known. So this is what you're indicating is as the. So there are some works which do this. So some sort of feature representation of your internal data is still maintained, so that the global model is still good with the local update, but not extensive work there. Not extensive work. There's a recent ICML paper which does this, actually. So it preserves but it does not share this information to the global aggregator. It just has this information and the global representation in some sense, so that it compares and knows in which direction to update its local model, or how much of it needs to really update. Okay. So okay, one last question.
Yeah.
Okay.
When we talk about global aggregators,
Huh.
how global are we talking? And what is the implementation strategy? So suppose we have end users,
Huh.
all a specific group of user aggregators come together, make one aggregator, and then such aggregators also come together and make one global aggregator.
Okay.
Is it like that?
No, here I'm just talking about Google. So for example, in Google's example, there's only one aggregator, which is the company and its server, and all of us are clients. And even in the federated learning, in the Intel or the NVIDIA example also, it's the company which has the resource, and that's the aggregator. It's very hard otherwise to have such kind of resources, right? So it's typically a very rich company, rich organization which is hosting your entire system, and whoever are the customers or users, it's just one level of this thing. Right? Okay, so thank you very much. Good questions. Thank you.
Any final comments or any final questions? She will be around, so anyway, after this talk we have a break.
Please
so
feel free to reach out.
you can again interact with her. Okay, so let's have another big round of applause for Manisha.
Oh, okay, sorry.
A small token of appreciation.
Thank you very much. Thank you.
Okay, we will now break out for the coffee. Please be here by 10:55. Okay, thank you. You have your slides? You want to photo can I have on Monday? Because we have more people on Monday. Thanks.
I'll come back.
Sure. By the way, Jyotika, you are the session chair in the next session.
Yes.
Okay. So you are aware.
I'm aware of that. I have to
Okay, so I hope you had a great cup of coffee. So let's settle down and let's welcome our next speaker, Parthe. He is a Thakur Family Chair, Assistant Professor at the Center of Machine Intelligence and Data Science at IIT Bombay. He was a Simons postdoctoral fellow at UC San Diego. He obtained his PhD from UCLA and his undergraduate from IIT Bombay. He has received the AI 2050 Early Career Fellowship from Smith Sciences in 2024 and the Jack K. Wool Student Paper Award at ISIT 2019. So, over to you, Parthe.
Hello. Can you guys hear me at the back? Yeah. First of all, thank you to the organizers for organizing this wonderful workshop. It's a nice gathering of students and faculty members from around the country. And thank you for the opportunity to present this material here. This is a line of work that I've been pursuing over the last 3-4 years or so, and it's kind of come to some kind of a culmination. You'll see some of the results. So yeah, I'm going to talk about some fast first order methods for training kernel machines, and I'm going to jump right into the math. So if you don't follow, stop me and ask questions. It's sort of, things build up as we go, so it's important to have things clarified at the beginning itself. So here's the standard setting that we study in super. What we're given is n samples of data. Your data is some pairs of inputs and outputs, and the inputs come from some some domain omega. I'm going to assume that this domain is some closed and bounded compact subset of the d-dimensional Euclidean space. And I'm going to assume that the targets that I'm fitting the data to, the yi's, the outputs, are real value. Okay? And the goal in machine learning is really to find a function or a map f that takes you from your domain to the range, which is the real numbers, for any element in the domain, right? And yeah, the goal is that this function that you're proposing has to fit the data well somehow, right? And it also has to generalize well in some sense. So what's the standard practice? Is you want to minimize some kind of a loss function that depends on the evaluation of your function that you're proposing, or the model that you're proposing at the training points x1 through xn, right? This is the most general form of the loss function. Typically you write something which is a sum over f of xi and yi, right? That's the standard way of writing it. And then there is some kind of a regularization term that you want to penalize. You don't want functions that are too jagged, you want some kind of smooth functions, right? So another way to think about this is you're minimizing some kind of a data fitting term, and then some sort of roughness is what you're penalizing, and you want to minimize both of them simultaneously in some sense, right? So the decision variable of this optimization problem is f, which is the model that you're proposing, right? And the search space or the hypothesis space of this optimization problem is this blackboard edge. A very particular family of methods that is studied in statistics, applied math more generally, is what is called non-parametric regression, which is the following. The idea is that the hypothesis space is described in a very mathematically precise manner. Okay? But unfortunately, that is operationally a little vague, so it doesn't tell you how to do the optimization on a computer very nicely. But it at least is a very precise description of what the search space is going to be. Right? So here is an example hypothesis space. This is what is called the second order Sobolev space. Okay? So let's just parse what this expression here reads. So this is the space of functions which are twice differentiable over the domain 0 to 1. Okay? So this is a d equal to 1 case. These functions are 0 at 0, and their derivative is also 0 at 0. And the L2 norm of the second derivative of this function is bounded. So this is mathematically a very well described family of functions now. Okay. If I give you a function, you can check membership of that function in this family. Okay. But then it's not clear how you actually do optimization in the space of functions. There are infinitely many functions. Yeah, so that kind of is one of the challenges of non-parametric regression in practice. Yeah, all clear so far? Okay, so let's move on. There is a very specific type of hypothesis spaces which are called reproducing kernel Hilbert spaces, which are quite nice in the sense that they're mathematically as sophisticated as non-parametric regression, as sophisticated as they can get. But they also allow us to essentially apply all the ideas that we know from linear regression. There's a lot of clean linear algebra that you can use to explain what's happening in these systems. Right? So let's define what is a reproducing kernel Hilbert space. Okay. So for any a function space is a reproducing kernel Hilbert space if the following holds. So if you take any function f, right, and you evaluate that function, right? So f of x is the evaluation of the function. F is an element in the function space H. F of x is just a real valued number, right? Because these are real valued functions. This map of going from f to f of x is continuous in the function space, right? So I have a map that takes an element in this function space and it gives me a real number, right? Now if I were to make a small perturbation in the function space, that perturbation you have to be continuous in that perturbation. Okay? That's what we're saying here. Is that clear? Okay. And this has to be continuous for all inputs x in my domain, right? And it has to hold true for all elements in this function space. Okay. And why is this an important class of functions? Because of this reproducing property. Okay. And the reproducing property is the following: there exists for any RKHS, there exists a unique positive definite bivariate function k, okay, which satisfies the following equation. So what is this here? This is the dot product of two functions, right? So f is one function, k dot x is another function, right? The dot is the dummy variable of the function, the argument of the function, right? Yeah. And this is the function space is endowed with a dot product. Just like your Euclidean space is endowed with a dot product, the function space also has a dot product that you can work with. And yeah, the dot product of f with k dot x is exactly f of x. Right? So the dot product of two vectors is a real number. The dot product of two functions is also a real number. Are you with me? Okay. So yeah, this is kind of a more operational definition of the function space, which is that the set of all functions in this function space can be written as the closure of the span of all these basis functions k dot x. Right? So you take all these functions k dot x for different values of x. Right? You take all linear combinations of these functions, and that is the search space that you want to do optimization of. Yeah. Okay. So here is the kernel corresponding to the Sobolev space that you saw on the previous slide, right? So I said that every RKHS has a unique corresponding positive definite kernel k, right? And here is what is the expression for this positive definite kernel function, right? So k, x, z, x and z are two elements in my domain omega, right? And the expression is a little complicated, or I've written it in a slightly complicated form. It's not really complicated, it's just the integration of two polynomials multiplied with each other. And I've written it in this 2 minus 1 form because you can extend it to Sobolev spaces of arbitrary orders. They can be Sobolev spaces of order k greater than 2 as well is fine.
But in our cases, like order should be d by 2. So not all Sobolev spaces are cases.
Right. This is just for d equal to 1. Yeah. For d greater than 1, anyway, this expression doesn't make sense. Right? Okay, what's a positive definite a map? Is everyone familiar with what is a positive definite bivariate map? Yes, no, maybe. No, okay, good. So you have a bunch of points. Is it visible if I write here? Just tell me if it's not, I'll increase the font size. Right, so suppose you have n points, u1, u2, un, right? You take the evaluation of all ui, uj, right, for all possible I and j from 1 through n. This is a matrix of size n by n. Is this visible?
Yes.
Yeah. So this is an n by n symmetric matrix because the kernel function is symmetric, right? This matrix has to be a positive definite matrix, right? Then V transpose M V is always positive for all V in Rn, right? Okay, so we want to work in this reproducing kernel Hilbert space, and so we'll focus on in today's talk we'll focus on optimization problem of this type, where the search space is a reproducing kernel Hilbert space. Yeah.
Sir, before going there, can you just give the context? What's the use of reproducing kernel Hilbert?
It's a class of functions that we can learn. Just like neural networks is one class of functions we can learn. This is another class of functions that we can learn. They can be equally effective in many problems. Yeah? Okay, so turns out that even though the optimization problem is in an infinite dimensional space, so function spaces are infinite dimensional, turns out that the optimal solution to an optimization problem of this form has a finite representation. Okay? So there is a theorem called the representer theorem which tells me that any optimal solution to this infinite dimensional optimization problem must have a solution which is of this type, which is that f hat at any x is a linear combination of kx xi. Yeah. What are xi's? Xi's are the training inputs that you had in your data set. Okay. Yeah, this is kind of the kernel trick that you may have seen in an introductory class on machine learning. Turns out that kernels are really important in trying to understand what happens in deep neural networks, and that is why there is a lot of interest in studying kernel machines again. Okay. So this kind of a function is called a kernel machine. Yeah. We wrote a paper last year which showed that how should you choose the kernel function so that you perform as well as a neural network. Turns out that that is not a trivial task. You have to put in a lot of effort to actually find a good kernel function. But in today's talk, I'm going to assume that somebody has done that task for you already. They've given you a kernel function, and now you want to train the parameters of this kernel machine, which is these coefficients alpha I in the linear combination. Yeah. So yeah, today we'll be fixing k, and we'll learn how to solve this problem efficiently. Okay, so that's my old dog. Yeah, this is the old trick of solving or training kernel machines. So this is the way we do it. You take the optimization problem, which is in the infinite dimensional space, right? You apply your representer theorem, which means that any optimal solution is going to be of this form, right? It's going to be the linear combination of k dot xi, right? That's going to be the optimal function. And now you have an optimization problem in the coefficient space, in alpha space. This is a problem in n dimensions. You can use your favorite gradient based algorithm to solve it. Here is my favorite gradient based algorithm, gradient descent. So I can now optimize this loss function by taking a gradient with respect to alpha, right? And I will reach some kind of a minimizer. Right, so here is what the example looks like for the square loss, right? So if my loss function is the sum of squares of residuals, then turns out that this in the function space is equivalent to minimizing this in the coefficient space. Okay, kxx is this kernel matrix M that I calculated. It's the same thing, right? And now training this model is the same as learning alphas, right? Which is same as solving this linear system of equations. Right? This is an n by n linear system of equations where this regularization lambda is 0. Yeah, okay. And this is what gradient descent looks like on this optimization problem. There is a kxx term, and then there is the residual, which is kxx alpha minus 1. Nothing new. You've seen gradient descent before in some form. Okay? You can also do what is stochastic gradient descent. So you don't take all the data, only take a batch of the data. And then your stochastic gradient looks like this. So xb is some mini batch of data that you are taking. Right? So this is a fat matrix.
So x is full data.
X is the full data matrix, XB is some mini batch of my data. Right? So this is a fat matrix, right? And then I multiply by the transpose of that again, because that's what shows up in the gradient. But what's happening in the SGD is that I'm having to update all the coefficients, even if I'm running SGD on this minimization problem. So this is the old trick using first order gradient methods. So here is sort of what we would like any nice algorithm to have in a manner that allows us to scale to very large problem sizes. Okay. So we'd like the algorithm to be matrix free, which means that you never actually want to store this matrix M. Okay. What is the storage requirement for this matrix M? N square, right? If n is 1,000,000, you're already in trouble. N square is very large, you can't store it in RAM. Okay. So you want something which is matrix free. You also want something which is what is called batch friendly, just like deep learning is, right? You take a mini batch, you do an update, you process the mini batch, and you immediately have an update that you can do to the model. Right? You don't have to go over the entire data set to have an update. Yeah.
So do you want to also, are you fine paying order n cost per update, or do you also want some sort of coordinate descent type of a thing in this, where you only choose some coordinates of alpha to update?
I'd like something like that, although that is also order n, because inference on one point is also order n in this setting.
Can't you do Monte Carlo?
I can, but I want to also be generic in the sense that I want it to work for any kernel. I don't want to be specific to any particular family of kernels. And I also want stability. I want things to work at lambda equal to 0. I want things to work at low precision, and I want to use my hardware effectively. I want to maximize my GPU utilization, and so on. Right? So here are some existing general purpose algorithms. Yeah.
Sorry, just to confirm, this order n per iteration, you don't want that, but you're okay if that is necessary?
Yeah, I'm okay if that's necessary. We'll come up with a way to cut that down as well. Yeah. Yeah. So conjugate gradient is one general purpose solver for linear systems which have a positive definite matrix. That is not a batch friendly algorithm. I have to go over the entire data to actually make a single update. That's not nice. It's also very numerically unstable. It doesn't work well when you have low precision arithmetic. And then there is coordinate descent, which is another family of algorithms These are somewhat hard to analyze, and also they are a little hard to work with when you have ill conditioning in this particular matrix. I'll tell you what ill conditioning means here.
Why you are saying this is hard to analyze? What is this to understand particularly?
The analysis, translating the analysis into a practical algorithm is a little challenging. Maybe this is a personal opinion. Maybe there is a, there are sort of large unknown constants which I have to deal with.
So you are only working with positive lambda, right?
I'm working with 0 lambda.
0 lambda also?
0 lambda is not nice for coordinate descent algorithms.
Yes, you will not get exponential convergence.
Yes. Maybe ill conditioning is the more serious issue that I still cannot deal with cleanly in coordinate descent algorithms. Yeah. So yeah, hard to analyze is a personal take. This may not be globally true. Okay. So here is what my new show is going to be today. Okay, I'm going to reorder the devices. Okay. So what was the first device? Well, it was applying the representer theorem, which converted my infinite dimensional optimization into a finite dimensional optimization. And then I was using a first order method, which was in the finite dimensional space itself. Okay, what I'm going to do now is I'm going to just apply a first order method in the infinite dimensional function space. Okay. Now this is an algorithm which I can write nicely on a paper, but I can't implement on a computer. But turns out that you can actually implement on the computer because of the nice structure of the problem that exists here. And I'm going to then apply the representer theorem to come up with an update equation in my coefficient space that allows me to exactly track this sort of infinite dimensional gradient descent that we're running. Okay. Turns out for this class of problems, this can be done nicely. Okay. This is not a universal thing that you can do for all infinite dimensional gradient descent algorithms. Okay, so let's get started. Okay, here is what the main result is going to be. Okay, we're going to show the ability to train very large kernel machines, and we're going to be able to do that very fast. Okay, so until 2020, the state of the art was this algorithm called Falcon. Okay, this was not able to train kernel machines with about 1 million centers. Okay, it required a large amount of RAM. Yeah.
Center means data points?
Centers for now means data points, right? So it can't train a model which has more than 1 million data points in some sense.
This Falcon in Rosasco.
Yes, yeah, this is that group. We were able to solve for training a model with 1 million centers, but it would take a really long time. It would take 10 days to train a model with 1 million data points. That's ridiculous. And then this year we were able to figure out how to actually be a little stingy in how we pay the prices in each of the steps of the algorithm, and we were able to cut down the cost quite drastically, and we can now do it in 21 minutes. Right? Like this is a big gain that we're able to get. And in fact, this 700x faster is not really fair, because this is numbers only for 1 million, and that's how big we can actually run this model at all on the slow version. But the complexity is down from order p square to order p. Right? P is here the number of centers or number of samples. Okay, we'll see details on this through the talk today. Yeah. So yeah, this paper here is going to be at NeurIPS next year.
Some p times b or something.
It's like 3 times p. The large unknown constant is 3. Yeah. There is a large known constant, and that constant is 3. So it's not that bad. Questions? Comments? Okay, let's get started. So yeah, the first act is how do you actually do gradient descent in the function space? This is turns out not that complicated. If you know how to operate in Euclidean spaces, operating in a RKHS is almost the next immediate step that you would think of. This is a really nice textbook by Lowenberger on optimization by vector space methods. I highly recommend everybody in this room to buy this book and read it. It's a very nicely written book about a very complicated idea, but simplified down to something you can understand very nicely. Okay, so let's get started. I'm going to introduce some notation that is going to help me convey the ideas that I want to talk about today. So I'm going to think of this k dot capital X. Capital X is all my training inputs. Right? I'm going to think of this as an operator that maps from Rn to H. Right? H is my RKHS. And this is how it operates. So k dot x times alpha is exactly this linear combination of my basis functions, k dot x alpha. Right? For a vector y in Rn, I'm going to call the subvector yb corresponding to indices in B. Right? This is sort of what we do slicing in NumPy or Torch or whatever you use. Similarly, xb is going to be the subset of x indexed by b. Yeah? And f of xb is going to be the evaluation of f at each of those points in xb. Right? So I take the evaluation of f at all the xi's which are in b and then stack them into a vector in rb dimensions. Yeah? Okay, so we are going to use the generalization of the gradient in the function space, which is called the Frechet derivative. Okay, and the Frechet derivative is essentially defined in exactly the same way. So if j is a functional which takes an element in the function space and maps it to a real number, okay, then the Frechet derivative is defined just like you define a standard derivative. Right? This is the generalization of your directional derivative that you study in d-dimensional calculus. Right? And turns out that this is a linear operator on H, right? And this the gradient of J with respect to F is also an element in the RKHS itself. Yeah. So just like if you take a real valued function, you take the gradient of this function, you get an element in the space with respect to which you are taking the gradient, right? Okay. So similarly, the Hessian is also defined in the same way. The Hessian is now going to be a map from the RKHS to the RKHS itself. Yeah.
So this gradient being a member of the same RKHS, is that always true, or?
This is true for RKHS. This is true for all Hilbert spaces actually. Yeah. More generally, it belongs to the dual of the space that you work with, but Hilbert spaces are self-dual. Yeah. Okay. So here is what is the gradient of one term in my loss function, which is the square of the residual, with respect to f. Right. Let's apply what we learnt in 12th standard chain rule. So the first is the gradient with respect to the residual, which is f of xi minus yi, right, times the gradient of the one thing that depends on f, which is f of xi. Right. So you want to take the gradient of f of xi, which is a real number, with respect to f. Yeah. Okay. What is that? So we know that f of xi in a RKHS is the dot product of f and k dot xi because of the reproducing property, right? And the gradient of this quantity with respect to f is nothing but k dot xi. This is the generalization of gradient of a dot product x with respect to x is a. Right? This is the generalization of that in the functions. Okay. So what does my gradient now look like? In the new notation that I have introduced, my gradient on my square loss looks exactly like this. This is the k dot x operator, and to that I multiply what is the residual on all my data. Right? How do I get a stochastic gradient? I take a mini batch of my data indexed by b. Right? I similarly get this object, which is k dot xb. This is a map from RB to the Hilbert space, right? And what I multiply now by is the residual on those samples indexed by b. Okay? We are now ready to start doing all sorts of ninja tricks on first order methods in Hilbert spaces. Okay? So let's get started. This is what the stochastic gradient descent looks like in the RKHS. Okay? So I had my update equation here, right? This is the gradient descent update equation, right? I wrote down the gradient in the previous slide. That gradient was nothing but k dot xb times the residual on xb, right? I'm going from here to this line by applying my representer theorem, right? And this is what the update equation is in the function space, right? Now the question is, can I track this update in the function space in the coefficient space somehow? And turns out that the answer is yes. Here is exactly how you should track this. Okay. So the claim is that if you do this update in the coefficient space, you are effectively doing a stochastic gradient descent in the infinite dimensional function space. Yeah. So what is the update? You update only the coefficients corresponding to the b coordinates in the batch. Okay. And how do you update them? You update them exactly with the residual on that batch. Yeah. Okay. And turns out that stochastic gradient descent converges exponentially fast in an RKHS. Stochastic gradient descent converges exponentially fast in an RKHS under the condition that you can interpolate the data.
Yeah, but this is known for the
This is known
RDE also.
This is known for RDE also, but like in an RKHS you are guaranteed that
basically your claim that dual is hard to analyze is not true anymore. So if in RD I interpolate, then I can do basically very fast stochastic gradient descent with exponential convergence in dual space.
Yeah, you're right. Yeah. So yeah, the hard to analyze claim was maybe peppered a little too much, but the ill conditioning is the real issue in the.
Under interpolation, no. We can talk about it later. But like, what is kappa here? I just want to know.
Yeah, kappa here is the condition number of the kernel matrix. Okay, and that is going to be very large, and we want to somehow cut that down as well. Right? So if you want to train a model which arrives at loss epsilon, you need these many steps of stochastic gradient descent. Right? Kappa is the condition number of the kernel matrix. So what is the condition number? It's the largest eigenvalue divided by the smallest eigenvalue. All eigenvalues of this matrix are positive because they are a positive definite matrix. Right?
So now that I think maybe like if I under the interpolation regime, I run the dual coordinate ascent, stochastic dual coordinate ascent.
Yeah.
There is no difference in the algorithm.
I'm going to make things a little more complicated, and that's where things diverge a little. Okay. Okay. So this is sort of the point at which we'll start making things a little more complicated. We'll embellish the stochastic gradient with more fancy things like preconditioning. Yeah.
So this condition number, how does it change depending on the kernel? Like, is there any general? So, for example, if I use like quote unquote a stronger kernel, more nonlinear kernel, does that always increase the condition number, or?
It's not clear. The dependence on the kernel is not very clear. The dependence on dimension is somewhat clear, but yeah, the dependence on the kernel function is not very clear.
But is it any okay? So this is just question. But like you already have like eigenvalue decay of the kernel operator. Is it related somehow?
It is exactly that. So you take the first eigenvalue and the nth eigenvalue and you divide them. The issue is in the integral operator, you don't know what is the distribution with respect to which you are defining the operator.
Like if you have had tail kernel, then basically.
Yeah, you have an estimate of what the condition number is. When running the algorithm, you don't need to know what the condition number is, right? Yeah. Sorry, does that answer your question, Vikram?
Yes, so in this case, you actually want kernels which are, which have heavy tails, as opposed to kernels whose eigenvalues decay fast.
Right. So I'm assuming that the kernel is given to me by the data scientist. I'm just doing the job of training the kernel machine. I might be able to tell the data scientist that, hey, you need to choose a kernel that has a sloppy decay of eigenvalues.
Yeah,
but that is their task. I'll leave that to them to decide.
Because in practice, so if you take deep nets and look at their eigenvalues, like the ones that fit really well have steeper decay of eigenvalues, right?
Yeah. It's not quite clear exactly what how the eigendecay is related to performance.
Percent kernel eigenvalue decay quite fast, but then it doesn't work anywhere.
Yeah. So we'll address some of these issues about condition number in the next few slides. Okay. So yeah, we need to do something called preconditioning. Okay. To give you an idea of what the speed up looks like in sort of wall time versus the batch size. Here is the kind of behavior. So the x-axis here is the batch size. The y-axis is the scaling, the speed up that you're getting. I'm assuming a parallel computing model, that of a GPU, for example, which allows me to process many batches simultaneously. Okay? So turns out that there is some kind of a saturation to my linear scaling regime that I have. Okay, so I can't actually use batch sizes which are very big and utilize the entire GPU because of this saturation condition. Okay? And where it starts saturating is proportional to 1 over the largest eigenvalue of the kernel of the kernel matrix. Okay? So the largest eigenvalue is kind of my enemy here. It's not allowing me to go faster because it prevents me from having large batch sizes that allow me to take advantage of the GPU that I have. Yeah.
Is there some implicit normalization because the largest eigenvalue is?
There is a normalization. I'm hiding that. I want to keep only the dependence on the largest eigenvalue. So the units of this scale are not defined on purpose. Okay. So typically this is what the condition number looks like. It is something which is maybe exponential in n, but it sort of slows down as d increases. Okay. D is the input dimension. Yeah.
Can you explain what preconditioning was?
I'll tell you exactly what that is. But essentially the idea is that you want a dependence on kappa which is more friendly in some sense. Okay. Kappa as a function of n can grow very, very fast. You want to somehow slow it down a little.
So where did you fit this conditioning? Exponential?
This one?
Exponential.
So based on the decay rates of eigenvalues of integral operators, exactly. And so if I were to somehow reduce the effect of the top q eigenvalues, okay, and I were to be able to somehow say that the first q eigenvalues of my kernel matrix are going to behave like the q plus 1th eigenvalue of the kernel matrix. Suppose I make that assumption. Then the condition number suddenly reduces from sigma 1 over sigma n to sigma q over sigma n. This can actually be a very big speed up in q. Okay, so I can train my models much faster because this linear regime has now shifted from 1 over sigma 1 to 1 over sigma q somewhere. Okay. So it allows me to use the an optimal size batch size which is taking advantage of the GPU somehow.
Sorry, this might be a silly question, but usually the condition number is large because of the smallest eigenvalue being very small.
Right. That is the case here as well.
Yeah.
But that enemy I cannot handle anyway. So I'm going to work with an enemy which I can handle, which is the largest eigenvalue. It turns out that itself is much larger than sigma q.
So I just missed maybe. So can you just explain how did you get kappa q? What
Kappa q I am defining as the ratio of the qth eigenvalue to the nth eigenvalue. Yeah. And I'm going to come up with a preconditioned version of SGD that has a the number of steps it takes is kappa q times some constant rather than kappa times that constant, and that's going to give me a speed up which is exponential in q in some sense. Yeah. Okay, so how do you do preconditioning? This requires you to now start working with the Hessian of the kernel matrix somehow. Okay. So this is the preconditioned stochastic gradient descent algorithm. I only apply a preconditioning operator before I take the gradient. Okay. And how do I define my preconditioning operator? I need to look at the Hessian of the loss function. That Hessian is exactly this operator. This is a rank n operator. Okay. This is the equivalent of UU transpose. Okay. Just like UU transpose is a rank 1 matrix. This is k dot xi outer product k dot xi. The generalization of UU transpose. Okay, and let's sigma I psi I be the eigen pairs of this Hessian. So h psi I is sigma I psi I. Right? Then I'm going to define the spectral preconditioner as the identity operator minus some sort of downscale projection. Okay, this is a standard spectral preconditioner which people use in numerical analysis. What this does is, if you now look at the largest eigenvalue of the preconditioner times the Hessian, that becomes sigma q. Yeah.
We have access to the sigmas.
We have access to the sigmas.
We know the sigmas.
We know we can calculate the sigmas.
So you have to do SVD.
I have to do SVD.
That's NQ was it?
I'll tell you exactly how that works out. So this is
Previous slide.
yeah.
And we also know this psi.
You know the psi is as well.
So same like SVD.
Just like SVD, yeah. This, you do an SVD on this operator. The A transpose is this operator. A transpose A is your kernel matrix, right? You can do eigen decomposition on the kernel matrix. That gives you all the eigen functions of the dual operator A transpose as well. And that allows you to do all these computations exactly. So it turns out that when you do this SVD, you know what psi i's are going to be as a function of EIs, which are eigenvectors of the kernel matrix. This is computation I can do. Like you said, this is really expensive, but for now, let's just see what that algorithm looks like when I actually track the action of the precondition stochastic gradient. This is the algorithm I get. So this was the stochastic gradient update. And now I have to do an additional update, okay, which essentially takes the residual on my batch, multiplies it with a low rank operator, and makes a correction, additive correction to all the coefficients in my in Rn.
So overall your algorithm has become expensive.
Yeah, I have. Yeah. Go ahead.
Is it fair? This is almost now like a quasi-Newton.
This is a quasi-Newton exactly. Yeah. But Q is much smaller than N. So, but yeah, it is quasi-Newton. So,
but the quasi is
so now you may say that I am lying because I said I'm going to only do first order methods. This is a quasi second order method. You're right. Yeah. 1.5. Yeah. Okay, so here is what the algorithm is. This was the first eigenpro algorithm that was proposed in 2017. It has an initialization cost which is quadratic in N because you have to do the eigen decomposition.
So N square Q comes from?
N square Q comes from finding these eigenvectors, right? The number of flops per sample is something like this, okay? And then the amount of memory you need is you need to store this preconditioner vector E, and that is you have a memory blow up in some sense. You don't want to have a memory blow up. That is not a good algorithm, but this is a starting point. We'll now cut costs quite ruthlessly actually. So here is what we do. Instead of working with the entire kernel matrix, we work with some submatrix of the kernel matrix. Okay, you calculate the eigenpairs on that submatrix. Okay, the size of this submatrix only has to be logarithmic in n, polylog in n. Okay, when you do that, you now get an approximate preconditioner. Okay, and now you work with this approximate preconditioner. You do the same algebra. Now the updates become the following. You had the original updates on the mini batch. This is just the stochastic gradient descent. Now your preconditioning involves updating coefficients corresponding to samples which were in this submatrix that you used for preconditioning. Okay, so only log n samples are getting updated for preconditioning. This now has a setup time which is logarithmic in n. It has a memory requirement which is the extra memory requirement is also logarithmic in n. Okay? This is the second version of eigenpro.
This converges just because of the square loss.
This converges because of the square loss.
Because of Cauchy Newton is like beyond the square loss.
Yes. Yeah. So for now, stay with square loss. It turns out that the idea is clean enough that it extends to other smooth convex loss functions also.
Is another reason for convergence is because whatever the quasi-Newton what one is doing, it sort of is still within whatever are the Lipschitz bounds allowable by the gradient descent algorithm.
Yes.
And so
the
then,
Lipschitz bounds just don't change because you're with the square loss. Life
so
is
then
good.
it's basically a gradient descent with a
Yeah. Right. Correct. Okay. There is one problem though, a big problem actually, which prevents using kernel machines on very large sort of data. It's that the inference time is O of n being the size of your training data. This is not nice. And the memory at inference is also n. You have to store all your training data to do inference. This is as good as having a lookup table of sorts. right? This is not a nice thing in some sense. And so people use what is called an inducing points kernel machine, which is the following approximation. They choose some points zi in your domain, right? And take a linear combination of k dot zi times beta I. Beta i's are some new coefficients. And now there are only p coefficients, and p is typically much less than n, right? And now you've sort of decoupled the training data size and the model size. So p is now your model size, and you can train on arbitrarily large training data in principle.
So this is P that
You choose p.
Like
You choose p. Right?
kernel thinning and stuff.
Yeah, exactly. You choose what p is, right?
So what's the typical size of P like?
So here is the plot that actually tells me I need large p if I have large n. Okay, so yeah, a big data set deserves a big model. This is kind of inspired by what we know from scaling laws on large language models also, right? Like just having a big data set is not enough. You need to scale the size of the models. So if here I am showing you the performance as the number of training samples increases, the test accuracy increases, of course. But if I were to increase the model size, I get a bump in performance, always. So if I were to keep increasing the size of the number of inducing points I use, I always have a better model that performs better than the smaller model in some sense.
So roughly square root of n.
That is based on like classical analysis. We don't believe that to be the case anymore, because empirically we see performance better when p is linear in n in some sense.
What do you mean by classical analysis? So you don't believe on the assumptions or?
On the assumptions in that analysis that give me root n. So that's based on some kind of uniform convergence kind of behaviors. Here we are dealing with interpolating models and so on. So it's not clear, because empirically we observe the performance is better when p is growing linearly in n and not
Even if you have
root
to
of.
approximate, let's say, distribution in MMD or something, like you have to approximate the distribution in MMD distance, discrete distribution. I think they have this bound, no, like this kind
Yeah. Those bounds are sort of not explaining what happens in practice, which
but
is
those
why
are
the
not like those are not uniform convergence.
maybe, yeah. Like there may be another family of bound. I'm not familiar with this one actually, but empirically we observe that p has to grow much faster than root n. Actually, we don't know why. We don't know what is the correct rate at which it has to grow either.
I agree like about this random feature work, because there they have strong assumptions, but at least this kernel thinning work seems like oh, like nice, like not
Yeah, I'm not convinced what is the correct order of p that should be, so I'm going to allow it to be a free variable. I'm going to allow the data scientist to choose what p is, whatever model that they can fit on their GPU, I will let them choose p. Right? And now the task is to train these big models. Okay, so now your training is essentially solving this rectangular linear system of equations. Okay, and again we are going to set up the problem as an optimization problem, but now the search space has gone down from the entire Hilbert space to the span of these inducing points k dot zi. Okay, this is the training problem we are solving. Yeah.
Do we assume those p points are given, or is there some?
We are going to assume now, for now, that those p points are given. Of course, the choice of the p points makes a big difference. So if you do a k-means processing or a p-means processing before, and then use those inducing points, they actually perform better. But then it's a judgment call as to whether you want to pay that upfront price or not.
What if I just use randomly?
It doesn't work too badly. It's quite good. It's within 1-2% of the k-means. So you can choose randomly any points in the data set, and that gives you.
Yeah, I mean, large enough, then you're already in the last.
So here is what the challenge is now, that the gradient is still going to look like this, right? Which means that this is no longer in my search space, okay? And I only know how to represent functions in my search space in the form of k dot z beta, right? This is the search space. Right? So how do you do this? The standard idea from optimization is you take a gradient step and then you project onto the search space, right? So when we did that, after a lot of bookkeeping, essentially we figured out that here is a lemma that tells us what is the structure of the projection problem. So if I were to, because I am in the function space.
Where did you find it?
So I project onto Z. Z is the search space, the span of this span, okay, the model space. Okay. So I want to project onto Z, and because I am in the function space, I don't know what is the geometry of the function space. The function space only knows one norm, which is the RKHS norm. So I'm going to take a projection in the RKHS norm. Okay. And turns out that the solution of a projection, okay, so if I were to project G onto this space, G is any function in the RKHS, then the solution is of this form, k dot z times b, and this beta is the solution to this linear system of equations. This problem is just the same as the first problem that we saw, right? Training a kernel machine, but now with p samples instead of n samples. So the projection subproblem I can solve by invoking eigenpro2 again, and that is what we do. So here is what the inexact projected stochastic gradient descent looks like. Thanks. I have to still pay some setup price that is negligible. My cost, the memory is now is independent of n, which is great. I can scale to arbitrarily large data sets. But the price that I pay for processing a mini batch is quadratic in P. And that is because I have to solve this linear system of equations at every step of the stochastic gradient descent. Right? This still works in the sense that it allows me to now train models which are very, very large, models which are a million samples, million inducing points large. This was not previously possible until last year. Okay, I'll sort of skip through this, and I'll just quickly share what exactly we do to speed things up. How do we get the cost down from quadratic to linear in the number of inducing points? Turns out that the projection step is the most expensive step. Okay, so how do you cut costs when you have one expensive step? You sort of batch the processes until then, and then you pay that one big bulky price together. So that is amortizing the cost of your projection. So what you do is you do delayed projection, and the algorithm starts looking more and more complicated, but this is just nothing but just a bookkeeping exercise. In principle, in the function space, you're just doing a delayed projected preconditioned stochastic gradient descent. Right? Theory exists for all of this cleanly. No new theory needs to be defined about their convergence and all that. What it does is that the number of flops per sample is now linear in P, and the memory requirement is going to be linear in P again. This allows me to train models which are very, very large. So here I am showing you the performance of the three algorithms. So Falcon is sort of the competing algorithm, or what used to be the state of the art. EigenPro 3 is the algorithm which was taking, which was doing a projection at every step, and so it used to take us 10 days to train a 1 million model, a 1 million inducing point model, and now we can train it very, very fast in 20 minutes on one GPU. So here is a list of all the different papers that made these little contributions at each step, and here's the diff that each of them has introduced. We also were able to plug in momentum in the function space. It turns out that adds more bookkeeping load, but it allows you to bring down the steps to root of square root kappa instead of kappa. So that is another big improvement that we can get. We're still working on the case of smooth convex optimization. Turns out it's not too hard. We just don't know how to express this object cleanly, so I've left that as parts. The number of steps that I need to run my stochastic gradient descent for. That object is, it's not clear which condition number I should be using anymore, because the condition number is changing as the iterations proceed. And the Hessian is changing as the iterations proceed. Square loss has a fixed Hessian. Logistic loss doesn't have a fixed Hessian.
Let's talk
Yeah.
So SGD with momentum, does that become unstable?
It doesn't actually. It's quite stable. No. Because this is a convex landscape in the function space, so it never becomes unstable.
So basically, this is kind of getting accelerated rate in the dual space, and again like
Accelerated rate in the primal space, in the RKHS.
yeah, but I mean this accelerated rate. So this for interpolation, you can show that
In the dual coordinate ascent, you can show this rate as well. I don't know how easy it is to plug in preconditioning, but that is something that we should think about. Yeah. Okay, so here are some open questions that I want to end with today. So we were able to train these very large kernel machines, and they this is now sort of solved a problem. You can train these models at very large scales. That was just not possible before. So nobody ever knew whether these models are competing with neural networks or not. Maybe they are. We still don't know how to choose how many centers you need and how to choose those centers in a scalable and efficient manner. My hunch is that for preconditioning, we had a log n factor. We can cut that down to linear constant factor as well. And yeah, this sort of philosophy of just looking at algorithms in a convenient space where convex optimization holds is not a new one, but it's worth revisiting. We did the thing for RKHS. Can we do the same thing again for other types of spaces? Can we do the thing for neural networks? Does that give you new training algorithms for neural networks which are much faster and utilize the GPUs much better? And there are many new algorithms that have been developed over the last decade, RMS prop, Adam, shampoo, and whatnot. What does the new show look like when you use those algorithms? I'm going to stop. Thanks.
Questions? Okay, I can give you some incentive of asking questions. If you ask question, you will get a nice photo clicked, which you will get delivered in your inbox. Now, questions? No questions? Everybody understood? Then you should ask questions.
I will ask. So this image like practical question. So did you compare this ImageNet on like ImageNet with neural network performance? Can I just take the number?
Yeah. So actually here we use some. I think we didn't do it on ImageNet yet because it's a multi-class classification problem.
Okay.
The number of parameters I need for multi-class is P times C, where C is the number of classes. I don't know how to cut that cost down yet. So once I figure that out, I'll maybe think of ImageNet. But for now, we're looking at WebVision and CFAR 10, and these are sort of fewer number of output classes. Right?
So, and which kernel?
These are all with the Laplace kernel. So,
and it is clear like winner amongst like all the kernels.
Among all kernels, Laplace kernel is always good. No, actually, that's not true. For image data, you can do better with these convolutional kernels, convolutional neural network Gaussian process kernels, and convolutional NTK and kind of things.
That's again like a black box that I know.
Sure, but like any kernel is a black box.
Not Gaussian.
Sure, you can understand those other spaces also quite well now. People have done some work on looking into that. Those kernels actually perform better, but they're computationally expensive. So calculating one kernel function itself is quite expensive. And so
even the NTK is quite high.
to compute or to interpret?
To compute.
Yeah, it's much more expensive than the Laplace kernel. Laplace kernel is very cheap. And it's almost always better than the Gaussian kernel.
Who wants a nice Insta-TP? Questions? No questions? Okay, if there's...
I'm just curious about the numbers there. So when
Yes.
we have, I mean, the first two models at least has a difference of 1 million. I mean, in the space of P equal to 64K or in the space of P equal to 128K. And N is 5 million and 6 million for this. And this. But when I see the difference, the time is going down for Eigen Pro 4. Like from 5 minutes to 3 minutes, 5 minutes to 4 minutes. So.
Where is it going down?
I assume that it is going down.
Right. So the dimensionality of the data sets is different. So this is CFAR 5 million star and this is CFAR 5 million. So this is CFAR 5 million.
Yeah, but I'm trying to
some
understand what is making the time go down even if we increase N.
Right. So I'm telling you that the data sets are different. So the kernel computation takes different time on both data sets. That's the reason for the time difference.
It's just fascinating to see the difference actually. 5 million, 6 million and 5.2 million. The time is like, I mean 1 minute also. I'm just expressing my fascination at it.
Right. And the reason is that these are just different data sets. So you have to do kernel evaluations in the algorithm, right? The kernel evaluations take different times for different data sets. That is the reason. So the CFAR 5 million star involves a pre-processing step, which involves passing the image through a neural network. That is also what I'm reporting here. That is the reason for the. Yeah.
I was just expressing the fascination at it, right? Thanks.
Thanks.
Any more questions? Okay, if there is no question, then thanks, Partha. Thanks. Thank you. Blockchain Monte Carlo output analysis for stochastic simulation. Recently, she has also been interested in stochastic optimization algorithms. Over to you, Dutika.
Do I press and hold somewhere? One button? Or?
Have a long list. Yes.
Okay. Can everyone hear me? Okay, very nice. So thank you for the organizers for inviting me. I believe I have the unique privilege of possibly being the only statistician in the room. Is there any other statistician in the room? Bona fide statistician in the room? Very good. Doesn't look very promising for my field. But I'm very, very happy to be here. And one of my hidden, it's not so hidden, one of my agendas is to convert every single person working in machine learning to come to the bright side, out of the dark side, into statistics. Okay, so thematically correct. I'm also talking about statistical inference for stochastic gradient descent. This is not my main area of work, but there was something that was very close to what I usually do. I work in Bayesian computation methods in statistics, and I found some similarities. And a few years ago, we looked into this problem, and I thought it would be relevant for at least this workshop. Okay. So Parth did an excellent job of mentioning SGD many times, and so now I feel like the first part of this talk will be extremely boring, but hopefully not as much. So I'll talk about SGD itself and give you a very brief bad introduction that you don't need. You probably know already enough about it, and then the second half of my talk I'll talk more about the actual work we did, which was led by 2 PhD students who are no longer at IIT Kanpur. They've graduated. Rahul is actually in IIT Delhi as a faculty, and Abhinek is doing his postdoc at NUS. Okay, so 2 parts. There's an introduction to SGD. If you know everything about it, take a nap, no problem. And then I'll talk about inference for SGD as well, and also discuss a little bit about what inference means. Okay. The talk is going to go from 0 to 100 at some point. So I'll start with like pictures, and then very quickly there'll be like math. Okay. So one of the fundamental problems in statistics, which has now been co-opted into machine learning language, but I regularly call regression, logistic regression, classification as just statistics, and you can hate me. It's okay. In statistics is identifying trends in data. So here is a very, very popular data set. Very simple. One, what you call target, we call response, and what you call predictor, we call covariate. Okay. So on the x-axis, I have speed of a vehicle, and a car is moving and brakes are hit, and so we are sort of determining how long the car will travel for after the brakes have been hit, and that's my response. Okay, or my target variable. It's a continuous target variable. And a fundamental problem is then fitting some sort of trend, right? For this, and we've discussed this in a lot of mathematical detail today, so I'll make it very annoyingly simple. I'm trying to figure out what is a possible relationship between the speed that the car was traveling and how long the car will continue to travel after the brakes have been hit. Okay, and I can fit various types of maybe non-parametric regression models or something else, maybe a very fancy neural network, but I could also just fit a line, right? And that's sort of one of the first things we do. So what is the best line that fits this data? This is one of the first things we learn when we learn about, let's say, regression or prediction, right? Let's fit a line. How do we fit a line? Well, we can try to fit that line. That's what, let's say, my 8-year-old nephew might think would be an appropriate line. Do you think this is a line of best fit collectively? No, right? It's not. It's clearly skewed way towards on the higher side. And I can then ask my other 5-year-old nephew, who might then tell me this line, right? Because he loves annoying me. And would that be an appropriate line? Absolutely not. Very good. So we're warmed up. And does this look like a somewhat appropriate line? Right? We have no mathematical proof for it, but this is one that nobody will hate me for saying that this line seems appropriate to justify a relationship between speed and distance in this particular experiment. Fair? Okay. How did we find this line? So do we know how I found this line? Yes? Can somebody tell me if? Trial and error, yeah, we can draw different lines and then see which one looks nice, yes?
Trying to find the loss function, minimizing the loss function.
Correct. Brilliant. So we are trying to minimize some sort of a loss function, and these are choices we are making. And sometimes when we're working with data, we sort of just go with default choices. But we can be careful. We can think about what loss function might fit the best. We're basically trying to figure out, on average, somehow I hit the next slide. We're trying to figure out, on average, can I minimize the distance between the line and the point? Now, distance is subjective, right? Minimization is not, right? So the distance is measured by my loss function, and then I just want to minimize that average loss. So what I can do is my data, there are two parameters in the previous example. The two parameters are what? Sorry?
Distance and speed.
If I'm going to fit a line, there are two parameters I'm trying to find that describe my line. Slope and intercept, right? So the slope and intercept of the line are what I'm trying to find. So that's exactly right. So there are two parameters, and so in the data are x, which is in this case just my speed, but also I have the number 1 for every data point, which is going to track my slope. Okay, so if you've dealt with like matrix behaviored matrix style model matrix setup, then x's, which are all your speeds, and then you need something to determine your slope, and then you have y's, which are your distances, and then I have my intercept and my slope. This is what I want to find, and what I want is I want to have a guess for this part, right, such that it is minimized in some way from the actual observed observations, right? So I want to choose beta 0 and beta 1 in a way so that these differences are small, but not for just for like my car, right? For all cars, right? Because I want a general trend analysis, so that's why I'm going to do an averaged loss eventually, right? So that in general, I might have various what you call features, and I call covariates. I might have various covariates, and for each of them, I have a slope or a weight, right? For each of those, and then I can do a linear combination of those, and so our betas are just saying, well, how important are each of these individual predictors to tell me about how much the car will travel. And then I take the squared deviation and I average it, and somebody said loss, this is my loss function, this is called squared error loss, right, or least squares. And I minimize that, sorry, this is a typo, this should be beta. Once I minimize that, that is called my beta hat. As statisticians, I will put hat over everything that's random. That's incorrect. Everything, I will put hat over everything that is that is an estimator of some parameter. Okay? And then eventually, this is one way of coming up with like finally my estimator. This estimator is exactly a quantity, the problem in practicality is that I might need to find this estimator. Like what its value is, I need to find the estimate having observed the y's and the x's. And so eventually, a lot of statistics and ML problems turn out to be optimization problems. Once you've set up what is your loss function and you've set up your actual problem, now you just have to figure out what solves that problem, and that often is an optimization problem, not always. Okay, so let me just now encompass what I gave you as a general statistical estimation problem, right? In like a general space, so I can use the general notation. So I'm going to call all of my observed data as this object here. This I believe is called zeta. I never know, but I typed it and it's called zeta. And so I will call this zeta. So the observed data, your x's and y's, I'm going to club together as zeta. And my parameter space is capital theta. What was my parameter space for my line? My parameters were beta 0 and beta 1, right? And so what was my parameter space? Somebody said it? R2, right? Because each beta 0 and beta 1 are an R and R. I'm not assuming they're restricted in any way. And so the parameter space becomes R2. Great? Yeah? If you understand, nod vigorously. If you don't nod, then I will assume you don't understand. Okay? So, understood? Yes. Okay, so lots of people not nodding. So my parameter space is capital theta, and then I will now define my loss function from my data, which is f of theta and the data. So I have my loss function over here. My loss function was a function of my data and my parameter, right? So it's going to be a function of both those objects. So in linear regression, my zetas are the tuple xi, yi, right? All of those tuples. So zeta I is going to be xi, yi, and the loss function for a single observation is going to be yi minus xi transpose theta. Now theta is my beta. Okay? But in logistic regression, which is like a popular classification problem, again the zeta i's could be yi's and xi's. Xi's are your predictors and yi's are your labels now, 0 or 1, right? And my loss function is then the negative log likelihood. Okay? And then you go ahead and optimize that. So what do we want to eventually optimize? Well, eventually what I want to optimize is the averaged loss, but averaged as measured by the distribution from which my data are coming from. Right? So it's the expected, minimizing the expected loss is eventually what I want to do. Fair? And I'm going to call that particular expectation capital F of theta. It's only a function of theta because I've integrated out my zetas. Right? So it's only a function of thetas. But I often will not have access to the actual distribution zetas are coming from, right? I often will not have access to that. So what I have access to are the actual zeta i's, which are my actual data observations. And so my first level of approximation when we do optimization is to approximate this expectation with a sample average. Okay, so that's my first level of approximation. And so eventually this is my parameter of interest theta star. Unfortunately, I don't have access to my actual distribution. So I approximate this theta star with an estimator theta hat, which is then minimizing my empirical average over my losses. Okay? Okay, very good. And my empirical average, this includes the 1 by n, is going to be called f tilde. Okay? There are problems in which I can actually obtain this analytically, like linear regression. I have an analytical solution. But for example, in logistic regression and various other complicated models, I don't have the optimization analytically available to me, the solution to the optimization problem. In which case, I might need a solver, and gradient descent turns out to be a very commonly used one. Okay? Again, both speakers mentioned gradient descent at some point. Okay, so let's look at what gradient descent looks like. So what is gradient descent? Well, in this particular case, I have f tilde, which is my objective function. Now my transformed objective function has gone from my actual unobserved expected loss
and it's become my empirical loss, right? The empirical average, and this is the object I want to minimize. Okay? And so if I want to minimize that, well, I can write, this is exactly what this object is, and my gradient descent updates in the following way. My next iteration of the parameter estimate is the previous iteration minus a learning rate times a gradient vector, right? And so what is actually happening here, this you've probably seen a version of this. So let's assume my beta is one dimensional and I'm in a linear regression setup, so I just have one parameter I'm estimating. Then this object here is just a parabola, right? Yes? Okay, very good. And so this is just a parabola. And if I set my iterate, let's say at 1.6, gradient descent essentially works in the following way. It says that whatever is your eta t, the learning rate you've set, I'm going to approximate this by a convex function that has curvature eta t, and the minimization of that, the minimizer of that convex function, sorry, the quadratic function is going to be my next update. But visually it looks like the following. I'm just going to take a step in this direction on the tangent line, in this direction, and roughly the size of the step is eta t. Not exactly, but that's what I'm doing. Okay? And I keep going down in this particular space, hopefully not too much, as long as eta t isn't too large, and I can go somewhere there, eventually reaching very close to the minima, right? And I can set a criterion up as to what determines my convergence based on, let's say, whether the gradient is 0 or not, or the size of the updates are sufficiently small or something like that. Okay? So we've seen a version of gradient descent that looks like this. Okay? There are lazy necks in the room. Yes? Okay. All right, but in some situations, for example, if I look at my, sorry, this should be capital F here. If I look at my gradient vector, well, this turns out to be a sum of each of these over here, and in the often found situation that if n is very large, then at every iteration I'm going to have to calculate this object here, right? Now this part is a scalar, but I have to do a multiplication here, and then there's a multiplication here, and then there's a summation over all of these, right? Which can be expensive, right? And in linear regression, it's not that big of a problem, but in other more complicated models, that the gradient calculation can be very expensive. Another issue is that it's possible that all of my data is not available at the same time, right? So part of it we saw in federated learning, where there was data was being collected and coming back, and there was something happening iteratively. Data was being obtained iteratively. And so data may be coming one by one, which means I don't actually have access to this whole object at one time, right? So the story is that the gradient cannot be calculated, right? One way or the other, either because of computational issues or the lack of all the data being available, I can't actually calculate my gradient. Okay? So what do we do in this case? We approximate the gradient. How do we approximate the gradient? With whatever data we have, or we could do something really silly, is just with one observation, right? If whatever data we have are really large amount of data, then even that can be expensive, right? And we understand that we might have to do the update multiple times, right? And so this is where we do stochastic gradients. We can then replace the full gradient, by just the gradient from just one of these observations. Now, this whole thing is an average of n numbers essentially. My guess for the average of one number, a very bad guess, can be one of those numbers, right? Correct? And so that's about it, right? So I pick a random observation j sub t at time t, and then I approximate the overall average with the gradient from just one observation, the jth observation that I sample, okay? And so that's exactly what my gradient vector is going to be, okay? Correct? And so the part that is stochastic in stochastic gradient updates is actually the data that is stochastic, but then more refined to that, it is my actual objective function that's stochastic. Fair? because every single time my function is changing. Okay? Every single time I'm using gradients from a different function. So my actual function I'm minimizing keeps changing. Okay? So this is what this looks like. So for example, we saw a gradient descent. The actual objective function is still in black. That's my original objective function. But now what I did is in the first iteration, this is where I'm at. My blue dot, my beta value is 1. And what I do is so my original gradient descent would go up till here and then calculate gradients here, right? But what stochastic gradient does is it draws one observation, which was this jth observation, and draws the objective function for that. And that's my orange objective function, and says, okay, I'm going to take a gradient from here instead of here. So this is my estimate of the gradient. Okay? And then it's going to move to somewhere, let's say here, because it's going down in this direction. So the next iteration is going to be somewhere there. And look, it's somewhere here, but in the next iteration, my function has changed again. Right? So my objective function has changed again, and so now this is my objective function. And now according to this is not, it's fairly flat. So it's not going to make that big of a move. So it doesn't move that much. And so it moves a little bit, but now my objective functions change. So now it's going to take gradients from here. And now it's going to move a little far away because the gradient is fairly large negative number here. Right? And so similarly, it's going to keep changing the objective function. Right? Which is why the iterates have some sort of volatility in them, because my objective function keeps changing in every iteration. Fair?
How does that function get determined?
So what are we doing when we're doing stochastic gradient descent? I have a bag, my bag has observations, right? My actual data point. So in gradient descent, I take all the observations in my bag, and I averaged, each of those observations gives me a loss function, and I average all of those loss functions, and that's my black curve. In stochastic gradient descent, I pick one observation from that bag, and I say this is my loss function. I take the loss function from those set of observations, and I make that my loss function. Right? So it's sort of like saying that I will only pick one observation it is exactly like saying I will pick one observation from my data set and assume my data set has only one observation. Okay? And then what is my loss function? Just yi minus xi transpose beta is my loss function. Sorry, squared, the gradient of that is my loss function. Okay? I can also do a mini batching in this, where I can, instead of taking one observation, take a couple of different observations and then average the gradient from that. Yeah.
For a non-convex how does SVD do it outliers? Because it can show away the...
Yes. So for a non-convex objective function, this is where SGD is actually useful, is because you're always changing the objective function, you might actually deal with an outlier which makes you go away from where you were before, and in that case you escape a basin that you were possibly stuck at. So even when you have a low number of observations and you can calculate the gradient, if your objective function is non-convex, because of the stochastic gradient updates, you're able to escape out of a basin. Yeah? Okay, cool. So what do I do then after that? Well, I take all of these. So by the way, these iterates are mapped on the y coordinate just to show you the gradient direction. But the actual iterates are just on the x coordinate, right? Because they're just the beta values. And I assemble all of the beta values, and I can plot something. I can plot as time increases. Okay. As time increases, I can plot in black what are my actual beta t's. So in black are I should have put a legend here. In black are my actual beta t's as a function of time. But in blue is my running average of the betas, and not just the actual iterates. Okay? And so this is where I will deviate a little bit from what is usually done in SGD as far as I understand. So after running some, let's say, capital N steps, I finally end at some, let's say, beta n, which is my last number, right? And so I can say that my estimate of beta is beta n, Or another thing I can do is if I track this average, I see that this average is also, this blue average is also stabilized very close. And so I can also pick up a running average, and at the end I'll just get like a sample mean of all of those betas. Right? And particularly if you fix the learning rate and you don't make the learning rate diminish, then you essentially have to pick up the averaged iterates. Because you're not changing the learning rates, it's just going to keep going like this, right? The SGD iterates, then you have to pick up some average. Okay, and I will ignore this gal over here, and I'll only focus on this gal. I'll just focus on beta hat ASGD, A for averaged. Okay. Great. What do I do with this now? I'm done, right? So what happens is I take this and I say, well, I'll keep it in my pocket. I'll put it back in my model. I can do predictions. I can do classification. I can do all of the fancy things. I can show in a paper that, look, whatever model I built has a 0.02 improvement in prediction error, right? I can do all of those very nice things. What else can I do with this? That's it? Let's go home. Yeah, lunch. Anything else we can do with this? Anything else we would want to do with this? Teach me your ways? No? Is that it, right? Okay. Well, great. Then I have something to talk about. So what else can we do here? What we can do is something loosely I call inference. It's not traditional inference. And it is the following philosophy, that there are a couple of different sources of variability when we are calculating the SGD approximation to my actual parameter beta star that I'm estimating, right? The first source of approximation is the fact that we are using stochastic gradients, correct? What is the second source of approximation? The first is correct, right? That we are using stochastic gradients, and so that's a problem. Maybe that we want to address, that a different iteration of the same objective function optimization can land me a different estimate, right? Is there a second source of variation? Average where?
Finally, when we are trying to find the parameters, averaging.
So you're saying this step here?
Yes.
Yeah, so yes, this is, but if I'm given a different stochastic sequence of betas, I'll get a different average. But if I'm given the same set of betas, I'll get the same average, right? So there's no stochasticity in this operation per se, right? So where is there stochasticity anywhere?
Order of excise.
The order of excise. What do you mean? How we are sampling. Yeah. So that is the stochastic gradient, right? So the way we are choosing the excise is how is the stochastic gradient being impacted. Okay. So there was another level of, the first level of approximation I made way back in the Stone Ages, here was this, right? Is that I was actually interested in minimizing the expected loss over the data distribution. Because my goal is not always just to minimize training error, right? This minimizes training error. If I can genuinely minimize this, then this also talks about both training and test error, because it talks about all data that appeared in this way. Correct? This only talks about I have been given this data, I will minimize this error. But this talks about all possible data of this kind that can occur. I want to minimize the error there, right? So this also speaks of test data, as long as your test and training are from similar spaces, right? And so this also is something, is a level of approximation I made. Okay? Brilliant, very good. Okay, and so this is where what we want to do, and as a card-carrying statistician, one of my jobs is to give you uncertainty estimates in what you do, right? That's probably one of the #1 goals of statistics, is to provide uncertainty estimates along with point estimates. And so beta hat ASGD is a point estimate. It's one number on which you will do all your jaidat, you will give to someone. And you may not be comfortable doing that, given based on how difficult a problem is. And so what I do in my life is I give a margin of error and then Jaidad is on that margin of error. Okay? So we want margins of errors. That's basically it. So the nice thing about ASGD is that it has some nice properties, and this goes back to a fairly popular paper by Polyak and Juditsky from '92 that says the following. Now I'm going to assume a lot of things. I'm going to assume some smoothness conditions on F, which is essentially convexity, and a couple of other second order smoothness conditions. There's conditions on the underlying distribution that wherever zeta is coming from is a nice distribution, right? It doesn't have like unexpected outliers for which, I won't be able to do anything, right? So it has like nice tail properties. My learning rate is of the form some scalar eta times t to the power minus alpha, where so it's a polynomially decaying rate, but alpha has to be more than 0.5 and 1. Okay, so this is a fairly common object. And then beta star is going to be called my true optimizer.
Why did not we put like 0.5 and 1?
This is what Polyak and Juditsky, so their work says you can't include 0.5 because you will not get the following result that I will get. Well, they can't get the following result. I'm not sure if you will not get. There's no negative statement yet. Okay. And so then what is the result that they give us? They give us the following result. Now there may be some things you don't know in this, but so what this says is if I take my estimator, then how many of us don't know this notation? Everyone knows this notation? Oh, brilliant. Okay. So this means convergence in distribution. Okay. So how many of you know central limit theorem? Okay. So central limit theorem essentially says that averages, sample averages, not original data, but sample averages start behaving approximately Gaussian-like. Okay. Start behaving approximately Gaussian-like for some n large enough. So this is essentially a version of a central limit theorem. It's generally called asymptotic normality. That if you move the square root n that side and beta that side, beta hat ASGD is approximately a normal distribution with mean the true optimizer beta star and a covariance matrix that is this sigma by n. Okay, so it has a limiting known structure under some nice conditions. Okay. And this is like if a statistician sees this, it's like, it's like a birthday for us. So, oh, now I have a limiting distribution, I can do lots of statistics. Yeah.
Just smooth function or like other conditions?
So, there are some smoothness conditions. So, smooth is you have convexity as well. And then there is a second order condition as well.
So, strongly convex.
Yeah. It's not exactly strongly convex. So, there is some... we can chat later, but yeah, there is some restriction on how much is the convexity there. Okay, and so here so actually the nice thing is that this sigma is actually known, at least parametrically known. This is A inverse S A inverse. S is essentially like a Hessian matrix, and A is like a A is essentially like a Hessian matrix. And S is like your outer product style of your gradient vectors. Yeah.
F is your likelihood, aren't they equal to each other?
Yeah. So no, they're not because F is not, capital F is my right. So this is on my actual F, and what my distribution is coming from is capital F. So they're slightly different from each other. Yeah.
For the application of CLT, it is necessary that the variance needs to be bounded, right?
Yeah. So that's why I said this is not a CLT. It is what is called a general asymptotic normality statement. So a central limit theorem only applies to sample averages but there are other estimators also behave Gaussian-like, right? And so, but that's a very valid point. Some of those conditions are hidden under here. So when I say conditions on the underlying distribution, one of those conditions are that I should have enough second order, third order moment conditions. Yeah. But just to reiterate, this is not a CLT, it's an asymptotic normality. Yeah.
How is this different from asymptotic convergence?
This implies asymptotic convergence. So this is a convergence in distribution at a root n rate, and this implies that beta hat converges to beta star in probability. Yeah. So this is a stronger statement. Okay? And I should say that this is as capital N goes to infinity. So capital N is the number of SGD iterates. Right? So how many epochs or something that you'll run this for. Okay? Okay, the challenge is that these objects are very, very expensive to calculate. And so I'm not going to try to calculate this. Right? So what we want to do is something completely non-parametric. Which means I am going to assume I don't even know what this looks like and just try to estimate sigma directly. And there's a lot of work that people have done in this direction. But the first question is, how is estimating sigma going to help me? Right? Okay, maybe I didn't say this very well. I will estimate sigma. Okay? I will estimate sigma. Sigma is my margin of error for Jaidad distribution. Okay? So sigma is what I want to estimate. And sigma represents something, right? Sigma says that over repeated, so what does this convergence in distribution mean? And distributional behavior means over repeated such data sets, if you were to be given such data sets many times and repeat this SGD process many times for all of those data sets, your ASGDs that you will get from all of these repeated data sets will approximately have normal distribution centered around the actual optimizer with a certain covariance structure. If I can understand that covariance structure, which is basically tells you what variability you will have, then it will allow you to understand how much difference, what difference do you expect the estimator to have in general, right? I mean, what variability do you expect the estimator to have? Okay. So estimating sigma allows us to quantify this error, and I'll also give you, and so quantifying error is this philosophical object that statisticians, we would love to say, no, we must quantify error, But sometimes, and this is what my students and I thought about very carefully, what will we do with quantifying the error, right? Because the error sigma matrix is a P by P covariance matrix, right? So, and P typically will be large in realistic problems. So if P by P covariance matrix is a very large matrix, what do I do with this eventually? Okay, so we'll try to get to that answer as well. I have some insights, we haven't done a lot of work there, but there's some fun stuff we can do. But the key thing here, I think Manisha used the word independent and identically distributed at some point. I was very happy when she said it. But the key issue in estimating sigma is that what are my samples available to estimate sigma? The samples are actually my sequence of betas. That is behaving like my sample now. My original data are not my samples, right? Because sigma is the variability in beta hats, and beta hats were constructed from my betas. So my samples now are my betas, which are the actual SGD iterates. And these, these are coming from an update equation, this, right? So are the betas IID, are they independent? Right? Literally says the next iterate is the previous iterate minus something, right? And so this tells me that the betas are a Markov chain, right? But the problem is that because eta t changes every time, they are what we call an inhomogeneous Markov chain. So every time there is a different update rule, so it's inhomogeneous, okay, also or heterogeneous, okay. And there are other issues with this particular Markov chain. It's inhomogeneous. It actually doesn't have a stationary process that one can write down in most cases. And so it's inhomogeneous and non-stationary Markov chain. So it is a Markov chain just chilling in life. Okay? And I need to do something with it, right? And which becomes a little bit of a problem. But so there's this sequence of, so this is one core team led by folks in U Chicago and NYU, and there's another work that came using Bootstrap. But there's been more works in this space. So we did this work about 2.5 years ago, and so now there's been like at least 10 more papers, mostly in statistics, but nice different solutions for estimating sigma. Okay, so what is a very popular solution? A very popular solution, because it's very cheap, is the batch means estimator, which is how I got hooked into this space, because I use this estimator in my own work in MCMC, which is Markov chain Monte Carlo. Okay. So the idea is just the following: is I take my SGD iterates beta 1 up to beta n, and so these are all my iterates, and I put them into batches. These are not the batches of your mini batch. Okay. So don't think of mini batch when I say batches. These are different batches. Okay. The word batches can exist without mini batches. Okay. So these are just, you consider them as blocks if not batches, and there are capital M of them. But I'll do this in the following way. So people used to do this in the following way. They'll take a small batch up until A1 and take an average of that batch, that's beta bar 1, and then start the next batch which ends at A2, this is beta bar 2, and then the last batch ends up here at A sub m, and this is beta bar beta bar m. The way I've drawn this intentionally, these are going to be increasing sizes of batches. Okay. And so AM, the last iterate, is going to be capital N, and then BK, which is the size of the kth batch, is going to be the difference between this thing and this thing. Right? So it's the size of each batch, of the kth batch. And an estimator of sigma is essentially what looks like a sample covariance matrix, if you're familiar with this, of each of the mean vectors of the batch minus the overall mean, which is the actual average of all of that. Right? So it's just a sample covariance which is weighted by what was the size of each batch. Okay, that's it.
We just know that AM goes to N.
That's it. Yeah, we know AM equals N, and there is mechanisms of how to choose the size of each batch. And so that's actually the critical feature. Yeah.
Don't you want to wait for some time for it to burn in between?
Yeah, so all of that is pre-processing. So for example, I can set my beta 1 to be after post sort of stabilization. Yeah. So if you have I'm basically assuming a warm start at some point. Now the key here is that M over here and BK can dramatically change the performance of this estimator. I mean, you can go from miserable to fairly good very quickly. And the way you choose how these batches increase and how they work with each other also changes the performance critically. And so there was a lot of work chose this sort of, in the beginning I want things to be small, and eventually I want the batches to be large. And we were very perplexed by this. So for example, this particular paper does the following. It says, well, this we agree with. Each batch, the size of each batch should increase with n. This we agree that as iterates increase, I want to ensure that the size of the batch increases, because I want that, because each batch is mimicking my actual the SGD estimator, because each batch is an average. So I want eventually, as the batch, as the index increases, I want every batch to mimic the overall average, right? So I want that to increase. And so what they said is, let's use BK such that it's k to the power 1 plus alpha by 1 minus alpha. This is with some intuition that they had using autoregressive models. And this alpha is the same as the learning rate alpha. Okay? And so using this choice, BK increases as k goes to infinity, and they use this. This is the sole motivation. Where something fails, or where this choice sort of doesn't quite work, is eventually I want the size of each batch to be large, but I also want there to be enough batches. Because if I run out of batches, then I'm constructing a covariance matrix estimator with small number of batches, small number of observations, which doesn't give me good sampling quality. And so that's the other aspect of trying to choose, how do you choose a batch size, because there's a trade-off between batch size and size of batch.
A silly question.
Yeah.
So here each betas, they are dependent on the average of the previous or only the
No, the betas are the raw iterates. So each betas are dependent on the previous, conditionally dependent on the previous betas.
Can you reiterate what is the benefit of having a large batch size, and what is the benefit of having, in each batch size, maximum number of beta, as many betas?
Okay. So so what is my actual estimate? So what is this sort of doing? My actual estimator is A hat SGD, where beta hat ASGD, which is the overall average. What we are doing with batch means estimators is trying to artificially obtain more replicates of beta hat ASJD. How do you obtain more replicates of an average? Well, you consider a subset and create averages from those subsets and assume each of these subset averages behave like your overall average, right? That's the underlying assumption. But as n goes to infinity, beta hat ASJD also has infinite sample size. So each of these, the sample object, each of the sub means must also, in order to behave like this, have their batch size keep going to infinity. Otherwise, they're not going to be able to capture the infinite behavior. That makes sense? Okay, but the key that we found is the following, that this is not very surprising, but as n is going to now infinity, what happens is that you've sort of set the size of the initial batches. They're not going to change, right? So the initial batches, so as n goes to infinity, it's only the size of all but the last batch remains the same. So when more data comes in, all of the essentially bad batches in the beginning, because I don't have access to n equal infinity, the size of those remain the same, but it's only the last ones that I keep accumulating more, right? And so what we want, and so this is being sought because they would like to do this in an online way as much as possible. And so this works in an online setup, but then they're restricted by the size of the restricted in the way that the original batch sizes can't work very well. And so here's what we propose. This is equal batch size estimator with collapsing. So this is what our idea is that I'm just going to choose bk to be equal to b. So that means the size of the kth batch is not dependent on the batch. So every batch is of the same size, but as samples keep coming in, my batches will keep changing. Okay, so that's the key difference. Before the initial batches remain the same, now my batches keep changing. How do they change? Well, my bk is basically going to be the closest power of 2 that makes sense. Okay, and so it's c times 2 to the power kappa. Sorry, I shouldn't use kappa. Yeah, so delta is basically, so n to the power delta is like a polynomial rate, and I'm choosing a polynomial rate so that this is so that it's sandwiched between a 2 to the power exponent. Okay, so that's what I'm going with. So I will choose a delta and I will choose a c. Delta often I'm going to choose to either 1 by 3 or 1 by 2, right? So it's my etas are going roughly at a cubic or a square root rate. Okay, and so what does this mean? It means that in the beginning, when I have certain number of observations, these are my batches. After some iterations, when enough samples have come, these two batches will collapse to become a single batch. They're adjacent batches, double the size, so all I need to do is just average the means of these two batches, and then that's it. Okay. So as n increases, the size of my batch will also increase, and then we have some results. I don't want to harp on this too much, except for the fact that this what the kind of results we're trying to show, and all of this work is trying to show, is that eventually my sigma hat that you construct in this way will converge to sigma. The convergence is being shown in terms of L2 distance in expectation. So this is mean squared convergence, which implies convergence in probability. So you get some sort of an upper bound over here that is now going to depend on your deltas, and it's going to depend on your alpha. So alpha is your original delta rate, original learning rate, and delta is something you need to choose. Okay. So what is the delta we choose? So I misspoke earlier, Anand. The delta what we can choose is we can also analyze this bound. Although it is just a bound, we can try to analyze it and say, well, alpha is almost like a user's choice, right? Because the user wants to train their SGD, use a learning rate that works for the SGD problem. Conditioned on that choice, I want to find a delta, right? And so first, in effect, sigma hat converges to sigma in probability. And this bound becomes useful because in optimal delta I can choose as 1 plus alpha by 2. So it's like an average between your reduction rate and 1. Okay.
Does this part also depend on the dimensions?
So that's the other thing we want to do, is we want to be able to do dimension dependent analysis. Nobody's really tried that.
I'm just wondering, like, what is the high dimensional limit? Like,
So when we worked on this, we absorbed dimensions in the constants, because there's lots of these high probability bounds that are used, and then we just kept on absorbing them. That's usually what's been done. There's definitely we can tighten and at least get a dimension expression here. Yeah. Unclear. So it's unclear basically. Okay. And then C, the small c, which was like the constant next to this, we recommend, which was sort of obvious choice, is choose C so that the final choice is positive definite, because it's a covariance matrix, it should be positive definite. Okay. So something that we really wanted to do, which is why our doubling batch size strategy works, and this is what I sort of brought from our MCMC work, is typically what happens is all of these sigma hats, these batch means estimators, are very bias expressing. So they're typically underestimating the true sigma. So they're always sort of playing catch up. They're never able to accumulate all the variability. And because of that underestimation, if you're trying to estimate bias, I would rather trying to estimate a variance, I would rather overestimate the variance and guess that there is more variability than underestimate the variance and make some blasphemous error, right? So underestimating the variance is not something we typically want to do, or at least we want to underestimate less. And so I won't go into where this comes from, but through studying what are called spectral variance estimators and kernel lag windows, etc., one can construct an estimator that eventually comes down to a very nice combination of a batch means estimator with batch size 2b, which is the double of the previous batch size, and a batch means estimator of size b. But now this makes it really easy for us to use, because b and 2b exist very easily for us, because we have saved batches of the form of multiples of 2. Right? And so we can calculate a Lugsale estimator very, very easily. And you'll see some merits of doing that. And so this is like a simulation where we showed that if we do regular equal batch size estimator, we get a bias that is quite negative. And here you get much reduced bias. It's very similar to, in statistics, we have something called jackknifing. It's very similar to jackknifing. Okay. I don't have enough time, so I'll not talk about this. Let me just go into a couple of just quality of estimation. So what I do is I simulate some data from a linear regression model, which was shown to you before, and I have like some p is reasonably small here. I'm not really worried about size. I just want to look at quality, and beta star is a sort of like an increasing fixed iterate sequence. And so here's what I do. I simulate about 5 million observations from my actual model. I estimate sigma using the estimators of Zhu et al., which is the same batch means estimator but with different choice of batching. So I'm not going to talk about my confidence ellipsoids. I don't think I have time. And I'm basically going to check the distance of sigma hat from sigma intravenous naught. And because I want to be able to say that I'm fairly confident of what we did, we're going to do this 1,000 times and average over and provide some uncertainty estimates on our uncertainty estimates. Okay. This is coverage. This is norm. So this is my oracle. My oracle in this case is just sigma, because I know sigma in this. I can calculate it tractably. It's a nice linear regression problem. And so firstly, this is, unfortunately, it's called IBS, increasing batch size. So this is the Zhu et al. Increasing batch size setup. This is our EBS equal batch size setup. Now what you can see is that it's not as sort of smooth in terms of the error. And the reason is because we're doubling batches. As soon as we double the size of a batch, the number of batches reduces by half. Right? And so it sort of stays like that for a while until again the same thing happens. But then this is clearly then telling us that the number of batches has an effect on the quality of estimation, right? Because you actually see it go up and down. And then because we can lug sale the EBS, so that linear combination, and we get sort of reduced norm as well. The one thing to note, this is still a very open area, is that all estimators are bad. I mean, this is on relative Frobenius norm, and I've run it on, you know, 10 essentially 10 to the power 6.5. Essentially.
What do you mean by that?
I mean, I have run the SGD iterates for close to 5 million iterates. Yeah, 5 million iterates, and still I am fair amount of deviance distance away from my true sigma.
Okay, in terms of bound, like we match lower bound, or like there is a lower bound.
No, we don't have. We don't have that lower bound. We have an upper bound is all we have, but we don't have lower bounds.
This is in what dimension?
5. Yeah. So all estimators are not very good. This is a lot more work that we can do here, or maybe this whole area is just like not worth it. But I want to tell you quickly why it's worth it. Okay, you haven't scared me yet. Okay, yeah. Okay. Thank you.
Is the variance more like you expected? Or
Sorry.
Is the variance more or is it less? You said, right, it's better to estimate.
Yeah. So you let's see if we can. I don't have a I think I don't have a bias plot, but unfortunately we don't have a bias plot here. So this is Frobenius norm. So it's basically, you can think of it as breaking it up into variance of the variance estimator plus bias squared of the variance estimator, and the bias part is really what is the problem. The variance is not the problem, and not as much of a problem. And part of the reason is what is the data that you have to estimate the sigma. You have SGD iterates which are itself an inhomogeneous Markov chain, and those iterates, that data itself is not very informative. The way you can improve is if you run SGD on multiple parallel implementations for the same objective functions, you have then independent replications, and then you can do much better. But then that's a different machinery. I can't compare apples with oranges. Yes.
So you mentioned about inhomogeneous Markov chain system. So my university project currently involves working on solving combinatorial optimization problems using synergic tunneling, which uses both homogeneous and inhomogeneous Markov chain. So I just wanted to understand from your perspective, how does inhomogeneous and homogeneous Markov chain analysis differ in solving problems which are non-polynomial,
Yeah, so I can explain the following at least, that if you have an inhomogeneous Markov chain, the conditional distribution changes every time, right? So because the conditional distribution of every iterate is changing, anytime I'm looking, let's say, at the variance of a sum, to actually study that, every single expectation in there is different. Okay? Versus a homogeneous Markov chain, if I give me 10 expectations, all of them are one expectation, because they're conditioned on the same distribution. They're following the same conditional distribution. So it's sort of just the complexity and what tools you have available changes. Over and above things like if you have a stationary distribution or not, then is it a limiting distribution? If you have access to these, then you can at least make some simplifying assumptions that let's assume my process is stationary, like the starting from a warm place, etc. And if you can make those simplifying assumptions, then a lot of those expectations are under your stationary distribution, and then life is like beautiful.
Sorry, stupid question.
No.
Here the goal is so can we have bias estimated sigma?
So yes, so you can estimate. I can show you. I could have shown you a bias plot as well of sigma, like what is the of sigma hat, like how much is the bias. But this sort of gives you a bias plot for a very simple problem. It's a very one-dimensional problem. We plot what is the bias. This is like 0, which means unbiased. From positive, if it comes from positive, it would mean it's over biased. And so this shows you how sigma itself is under biased, sigma hat is under biased, and then sigma hat Luxial is a little less under biased.
So yeah, my question again, like very stupid question, but like you do in the mean estimation, right? This time estimation of
Yes.
So maybe some.
Yeah, so one of the things that I'm personally interested in is coming up with a loss function that is interesting for variance estimation. This is a very decision theoretic question. And so people have looked at Stein's loss, people have looked at check loss, people have looked at also something called confidence probability bound loss or something like that, where your optimal estimator of variance is not coming from mean squared error. In fact, like the sample variance is not the MSE optimal variance estimator. It's close, but it's deferred in some constant. Yeah, so that itself is a very interesting area that has applications everywhere. Okay, I just want to give one final punchline, which is probably the most exciting thing. So we also did it for logistic regression for the Santander customer transaction data. So here I have 200 features. I have about 2 million actual observations. My yi's, my likelihood is this Bernoulli-Logit likelihood. Okay, and then my loss function is the negative log likelihood loss function. So now the question that we wanted to ask here is, what do we do with an estimator of sigma? Okay, and so this is, and we didn't find many people giving us some answers, so we figured out, okay, here's something simple we can do. What do we do with, once we fit a model and we get theta, what do we do for a new estimator or for a new data point? We will take that theta and put it inside of this to get my probability of success, right? And then I can threshold that probability of success to guess whether it is a 1 or a 0, and that's my prediction. Well, P hat j, this is nothing but a function of my estimator, right? And this estimator has an asymptotic distribution, and this is a differentiable function. So statistics tells us that I can use something called the delta method, which says that now I have a distribution for each P hat j that accounts for the complex covariance structure in theta hat ASGD. Right? So this is like a simple application, like a homework problem in like a first level of a 400 or 500 level inference course. Right? We do this, and this has normal 0, and then I just get the actual pj, 1 minus pj squared, xi transpose, so the actual covariate for which you're predicting, and the sigma, which is the sigma that we've estimated. Okay? Now I have a margin of error for Jaidat here, right? I can construct a margin of error for this. So now I can do the following. I construct my predicted y's as p hat j's minus a lower bound. So I'll take a lower bound of the confidence interval for each p hat j's, and I say when this lower bound is greater than q, I'm going to call that my 1, my class prediction 1, otherwise it's 0. And then I get a misclassification rate without a confidence interval and a misclassification rate with the confidence interval, which is clearly lower. Okay, which means we've improved on the misclassification rate by accounting for the variability. But the key is, if I run my SGD iterates long enough, this SEJ will get smaller. Why? Because this should be capital N. Because this capital N keeps increasing. So if I run it for longer epochs, this gets smaller. So when this goes down here in the variance, my variance gets smaller. So eventually, when the SGD iterates get larger, this blue line should start matching the black line. Both of them will move, but the distance between them will get closer. So this is something we've done in MCMC, but what we could do is we could determine how to choose the number of epochs based on when there is no more variability to find. Right? Your black curve and blue curves are very close to each other, and so you don't have any more variability to find. Go ahead and stop on the number of epochs. Now you're just wasting training. Okay. Yeah. I'm definitely over time. She's staring at me. Yeah.
Have you considered using these confidence intervals for abstentions?
I don't know what that is.
So a classifier is not confident enough and refuses to make a prediction.
I see. I clearly have not tried because I didn't know this existed. But yeah, well, it sounds fun. Would like to talk about that. Yeah, I'm very curious on how we can take this into a general strategy of quantifying prediction error and doing that. Okay. Yeah. Okay. I'm sorry. I'm done. That's it. So we can do stuff with statistics in SGD. That's the bottom line. We can do stuff that is actually practically useful as well. If you want to read the paper, it's on archive. I think the JMLR link will come soon. It took us some 2.5 years, but we did it. But thank you.
Questions?
Could you use a low rank estimator for your covariance matrix?
Yeah, so I think
That's the natural thing to do in high dimensions.
yeah, so for example, all of that can come, sorry, this is the point, the problem with using a lot of pauses, is all of that can I think be done here. So this is, so people have done plug-in estimation but you know, this is being live streamed. I guess it's okay, I'll say it. Statisticians often don't necessarily worry about why. They're just like, oh, this is fun, let me show this result. And I care about why on good days. So yeah, one thing to definitely do is try to come up with approximations of this and this that are low rank very fast. And then, you know, whatever we're trying to do with these non-parametric methods would be would be useless. Yeah. Hopefully not, but yes, that's something to definitely do.
I'll go back and check how much the hits spiked at that moment. Yes.
So just so that I get it right, you said that the calculation of beta is stochastic. The estimate is stochastic, right? So we don't know what we are comparing the bias of sigma hat against, right? Do we know what are we comparing the
underlying, yeah, so we don't know in the sense that so this is where there's also like model misclassification. But if you assumed a model and you've assumed that your model is correct, right, that it correctly identifies the distributions, then you have access to possibly these objects. Like linear and logistic regression, you have access to S and you have access to A. Okay? And if you have access, then you can calculate. The problem is that these depend on parameters that are unknown. So which you may not know. So then you have to estimate those. And that's what is called plug-in methods, and that's what he's talking about, is also using some low rank approximations of those to construct those.
Any more questions? Okay, if there is no more question, let's thank Kritika once more.
Oh, yes.
Small memento from my side. Okay, I guess everyone is hungry after a dose of statistics. So let's break out for lunch and yeah, I mean, interact with others, interact with speakers, but please come back by 1:50. Okay, thank you.
I didn't send my slides. Should I do that now?
Yours is in the second half.
Yes,
yeah,
yes,
you can do it now.
Or can I actually use my laptop, because I have one GIF, only one GIF, which doesn't work on PDF.
You can save the PPT. Is it not open?
Keynote.
Sorry?
Keynote.
Keynote in the sense?
It's not PowerPoint, it's Keynote.
Oh,
It's
okay,
Mac
okay.
software.
So the thing is that then we have to stop the live stream.
Okay, I'll share the PDF. It's fine. It's just one GIF. It's not a big
because
deal.
everything is connected.